In a remote corner of southeastern Iran, a mountain that hasn't erupted since long before our species existed is rising, 3.5 inches in 10 months, sulfur pouring from its summit at 20 tons a day. Scientists thought Mount Taftan was dead. They were wrong. Today we're going to a volcano that slept for 700,000 years, a city of 100,000 people, sitting in its shadow and a hidden chamber of pressure, now searching for a way out. If you love stories where Earth itself betrays us, hit subscribe and stay close. Get ready. We begin. In the autumn of 2024, a Spanish volcanologist named Pablo González was scrolling through satellite data on his computer screen in the Canary Islands. He was looking at a remote mountain in southeastern Iran, a mountain almost no one in his field cared about. Then his eyes caught something that should not have been there. A patch of ground near the summit was glowing on his radar map, glowing in a way that meant the surface was rising. Slowly, steadily, like something was pushing upward from below. González leaned closer to the screen. He ran the numbers again, then again. The peak of Mount Taftan had lifted 3.5 inches in just 10 months. That might sound small, a pencil's length, but on a mountain that has stood frozen and quiet for almost 750,000 years, 3.5 inches is an alarm bell ringing through stone. To put that timeline into perspective, when this volcano last erupted, our species did not yet exist. Modern humans would not appear on Earth for another 400,000 years after Taftan's last lava flow cooled. Civilizations, languages, writing, the wheel, the pyramids, the entire human story unfolded while this mountain stayed silent. And now it was moving. The first thing González did was check his data for errors. Satellite radar can be fooled by atmospheric noise, by rainwater seeping into rock, by tiny shifts in the ionosphere overhead. Any one of those things could create a false signal of uplift. He cross-checked weather records from the nearest city, a place called Kash. There had been no unusual rainfall during the 10 months of swelling. He pulled earthquake catalogues covering a radius of 600 miles around the volcano. No quake larger than magnitude 5 had occurred during that window. He applied a noise filtering technique called common mode filtering to strip away atmospheric distortion. The signal stayed. The mountain was really rising. Then he checked something even stranger. After the 10 months of uplift ended in May of 2024, the ground did not sink back down. Most natural ground swelling reverses when the cause passes. A rainstorm soaks in and then drains. A small tremor settles, but Taftan held its new height like a held breath. That meant pressure was still trapped underneath. González picked up his phone and called a doctoral student working on his team, a young researcher named Mohammed Hossein Mohammed-Nia. Mohammed-Nia had first looked at this same volcano back in 2020. Back then, the satellite data showed nothing unusual. The mountain looked sleepy and ordinary on every scan. Something had changed in the 4 years since. The two scientists began working through the implications. If the swelling came from deep magma, the entire region around the volcano would need urgent monitoring. If it came from trapped gas building pressure in shallow rock, the danger could be even more immediate. Steam-driven explosions can happen with almost no warning at all. Either way, a mountain that geologists had filed away as harmless was suddenly back on the map. González sat looking at the radar image one more time. The glowing patch near the summit seemed to pulse on his screen. Somewhere beneath those quiet rocks, something was waking up. But what was actually moving down there in the dark? That answer would take the team into territory no scientist had ever mapped before. To understand why no one was watching this volcano, you have to understand where it sits. Mount Taftan rises out of a desert plateau in the Sistan and Baluchistan province of southeastern Iran. It stands 12,927 feet tall. That is taller than any mountain in the entire continental United States east of the Rocky Mountains. From a distance, the peak looks like a perfect cone, dusted with snow in winter and bare brown rock in summer. The closest city of any real size is called Kash. It sits about 31 miles to the south, home to roughly 100,000 people. Beyond Kash, the landscape stretches into one of the most isolated regions on the planet: rocky valleys, empty highways, villages where the same families have farmed and herded goats for centuries. To the east, just a short drive away, the land becomes Pakistan. To the south lies the Gulf of Oman. To the north stretches the Great Iranian Plateau. This corner of the world is called the Makran. It is a place where two enormous slabs of rock have been grinding into each other for over 50 million years. That grinding is what built Mount Taftan in the first place. The Arabian tectonic plate, the same slab of crust that holds Saudi Arabia, has been sliding underneath the larger Eurasian plate at a creeping pace of less than an inch per year. As it dives downward, it carries seawater and minerals deep into the hot mantle below. Those fluids melt the rock above them, creating bubbles of magma that rise toward the surface. When magma reaches the surface, you get a volcano. Taftan is one of those volcanoes. It is also the only one in this entire arc that scientists have ever considered active. 3 peaks form a chain along the Makran region, but 2 of them are eroded into rubble. Taftan still has its shape. Taftan still has steam vents at its summit. Taftan still smells of sulfur on a windy afternoon in Kash. For most of recorded history, almost no one paid attention to it. There are old reports from 1902 of smoke drifting from the summit. There is an unverified story from 1993 about a small lava flow that may or may not have happened. Beyond those whispers, the geological record is mostly silent. The reason for that silence is partly geographic and partly political. The Sistan and Baluchistan province is one of the poorest and most dangerous regions in Iran. Border tensions with Pakistan, smuggling routes, and tribal conflicts have made fieldwork almost impossible for foreign researchers. There are no permanent seismic stations on the volcano, no ground-based gas sensors, no tilt meters monitoring the slopes, nothing. Compare that to Mount St. Helens in Washington state, which has hundreds of instruments tracking every shiver. Or Mount Etna in Italy, watched by satellites, drones, and live cameras around the clock. Taftan, by contrast, has been watched almost entirely from orbit. That orbital view is what saved the discovery. If Gonzalez and his team had been forced to wait for ground sensors, the swelling might have gone completely unnoticed. The mountain could have moved through its first stage of unrest in total silence, with no one alive to record it. The next question was the harder one. What exactly counts as extinct, and how could a textbook definition be so badly wrong? Geologists divide the world's volcanoes into 3 categories: active, dormant, extinct. An active volcano is one that has erupted in recent memory or shows clear signs of life. Dormant volcanoes have been quiet for centuries, but still have heat, gas, or magma underneath. Extinct volcanoes are the ones science has crossed off the list. They have not erupted in over 11,000 years, the entire span of human civilization, and they are assumed to have lost their connection to the deep heat below. Mount Taftan was filed under extinct. The cutoff for that label is something scientists call the Holocene era. The Holocene began roughly 11,700 years ago, right when the last ice age ended, and humans started building villages, planting crops, and inventing pottery. If a volcano has not erupted at any point during all of human civilization, the rule says it is probably done forever. By that definition, Taftan was deeply, thoroughly extinct. Its last major eruption happened around 700,000 years ago. That is roughly 60 times longer than the entire Holocene. To call it extinct seemed obvious, safe, boring. The problem is that this rule was made up by humans who have only been watching volcanoes for about 2 centuries. Geological time runs on a completely different scale. A volcano can sit silent for 1,000,000 years and still have a churning chamber of molten rock waiting underneath. The label of extinct is a guess, not a measurement. A study published in the spring of 2026 by a team at ETH Zurich in Switzerland made this point with brutal clarity. The researchers analysed a volcano called Mount Taftan near Athens, Greece. They mapped its history across 700,000 years using tiny crystals called zircons. These crystals form inside cooling magma and can be dated using radioactive decay like rings inside a hidden tree. What the team found shocked them. During Mount Taftan's longest dormant period, a stretch of more than 100,000 years of silence, magma was still actively brewing underground. The volcano was breathing in the dark. It just was not breaking the surface. The senior author of that study, a volcanologist named Olivier Bachmann, called this discovery a warning. Volcanoes can hide for millennia without ever venting. The longer they hide, the more pressure can build, and when they finally do erupt, the explosions can be catastrophic. The implications for Taftan are immediate. If a Greek volcano can secretly stockpile magma for 100,000 years, what could a mountain that has been quiet for 700,000 years be hiding? This is the unsettling truth that Gonzalez stared at on his screen. The label of extinct was never a guarantee. It was a placeholder, a polite way of saying we have not seen this volcano move recently. As soon as the satellites caught Taftan rising, that placeholder shattered. There are roughly 1,500 volcanoes around the world that are considered potentially active today. Beyond that list lies a vast catalogue of mountains marked dormant or extinct. Almost none of them are watched closely. Almost none of them are checked with the tools that revealed Taftan's secret. How many of those silent peaks are also breathing? The answer to that question takes us deep underground, where the real story begins. On a flat sheet of paper, 3.5 inches looks like nothing. The width of a large man's hand, the length of a smartphone in your pocket, a pencil from tip to eraser. On the side of a volcano, 3.5 inches is a rule. Between July of 2023 and May of 2024, the summit area of Mount Taftan rose by exactly that much, 9 centimeters in the metric system. Most of it happened slowly, like air being pushed into a balloon by a hand you cannot see. At its fastest moment, the rate of swelling reached more than 4 inches per year. That kind of speed is not rare in volcanoes that are about to erupt. It is extraordinarily rare in a volcano that has been still for 700,000 years. To picture what is happening, imagine a steel drum buried just below your kitchen floor. Now imagine that someone is slowly pumping air into the drum. The lid of the drum bulges upward. Your floor tiles tilt, cracks open in the grout. From above, you can see the floor lifting bit by bit, even though the source of the pressure is hidden underneath. That is essentially what occurred at Taftan, except the kitchen floor was a mountain made of stone, and the steel drum was a chamber of trapped gas and possibly molten rock buried hundreds of feet below the summit. Most ground deformation events on volcanoes follow a predictable pattern. The surface lifts, and then it sinks back down. Pressure rises, then escapes, then balance returns. Geologists call this process inflation followed by deflation. It happens all the time at well-monitored volcanoes around the world. Hawaii, Italy, Iceland. Taftan broke that pattern. When the swelling stopped in May of 2024, the ground did not return to its original level. The summit area held its new height, held it through the hot summer, held it through the cold winter, held it as season after season passed and the satellites kept passing overhead. That refusal to settle is what kept the research team awake at night. A volcano that lifts and then drops is letting off steam. A volcano that lifts and stays lifted is storing pressure. The energy that pushed the mountain upward was still trapped somewhere inside the system. It had not vented. It had not dissipated. It was waiting. To find out where that pressure was hiding, the team built a 3-dimensional computer model of the mountain. They fed in every measurement from the radar satellites. They mapped the stress patterns. They calculated the depth at which the source of the swelling had to lie in order to produce the exact shape of the bulge they were seeing on the surface. The answer was unsettling. The pressure was concentrated in a zone roughly 1,600 to 2,000 feet beneath the summit. That is shockingly shallow for a volcano, far shallower than the deep magma reservoir, which sits more than 2 miles down. Whatever was pushing up the ground was almost on top of the mountain, separated from the open air by less than half a mile of rock. Half a mile. That is the distance from one end of a small town to the other, the distance you can walk in 10 minutes. A young geologist on the team described it like a pressure cooker buried just beneath the summit. The lid was the rock and ice of the mountain itself. The contents were either superheated gas, slowly rising magma, or some terrifying mixture of both. The question was no longer whether something was happening. The question was what kind of cooker we were dealing with, and how strong the lid really was. To answer that, the team needed to understand the eyes that had spotted the rise in the first place. 500 miles above your head right now, 2 satellites are racing across the sky at 17,000 miles per hour. They're about the size of a small van. Each one weighs roughly 5,000 pounds. They were launched by the European Space Agency, and they go by the names Sentinel-1A and Sentinel-1B. Together, they are the eyes that caught Mount Taftan rising. The Sentinel-1 mission is not designed to take pretty pictures of Earth. It does not capture sunsets or coastlines or snowy mountain peaks, the way a tourist's camera would. Instead, it sends out beams of microwave radio energy, bounces them off the planet below, and measures the signal that comes back. This technology is called synthetic aperture radar. What makes it powerful is that radio waves do not care about clouds. They do not care about darkness. They do not care about smoke, fog, dust, or weather of any kind. A Sentinel satellite can see the surface of the Earth at 3 in the morning during a thunderstorm, just as clearly as it can at high noon on a sunny day. For a remote desert volcano in southeastern Iran, where dust storms and harsh weather are common, this all-weather vision is a gift. But seeing the ground is only step 1. The truly remarkable trick is measuring how the ground moves over time. To do this, scientists use a technique called interferometric synthetic aperture radar, usually shortened to INSAR. Imagine taking 2 photographs of the same hillside, one this week and one next week. If you carefully line up the photos and look for tiny differences in the position of every pebble, you might catch a few inches of movement. Now imagine doing the same thing with radar signals instead of light, and being able to detect movement, smaller than the width of a finger, across an entire mountain range. That is what INSAR does. By comparing the timing of returning radio waves from 2 different passes, the system can detect ground shifts as small as a few millimeters. Over a year of regular satellite passes, it builds a complete map of which parts of the surface are rising, sinking, or staying still. When Gonzalez and his team applied this technique to Taftan, the summit lit up like a glowing dome on their map. The rest of the mountain stayed flat. Only the peak itself was moving upward, and it was moving in a perfectly symmetrical pattern that pointed to a single source of pressure underneath. There was one more challenge to solve. The atmosphere itself can fool radar. Water vapor, temperature differences, and changes in the upper layers of the sky can all bend the radio signals on their way back to the satellite, creating false readings of ground motion. To strip out this noise, the team used a method called common mode filtering. The technique works by comparing readings from many points across a wide area, identifying the patterns that match atmospheric distortion, and subtracting them from the data. After filtering, the signal that remained was unambiguous. The summit had risen. The rise was real. It was not a glitch, a weather artifact, or a measurement error. For the first time in human history, scientists had caught a forgotten volcano in the act of waking up, and the satellites kept watching, recording the silence that followed the rise. a silence that somehow felt louder than the swelling itself. What no one expected was that the next clue would come from the volcano's own breath. While the satellites were tracking the summit's slow rise, something else was happening at the surface of Mount Taftan that the team had not initially noticed. The volcano was breathing. Near the top of the mountain, scattered across a broad crater area, sit a cluster of openings in the rock called fumaroles. These are essentially natural chimneys, places where hot gases from deep inside the volcano leak out into the open air. Fumaroles are common features on active and dormant volcanoes around the world. They tell scientists that the underlying system is still warm, still chemically active, still connected to deep heat. Taftan's fumaroles have been hissing for as long as anyone has been watching. Steam, water vapor, carbon dioxide, hydrogen sulfide, and most importantly, sulfur dioxide, all pour out of these vents. On calm days, residents in the city of Kash, 31 miles to the south, can sometimes catch the faint smell of rotten eggs drifting on the wind. That smell is hydrogen sulfide. It is the volcano exhaling. During the same period when the summit was rising, between the summer of 2023 and the spring of 2024, the volume of gas pouring out of these fumaroles increased dramatically. The team measured sulfur dioxide emissions of roughly 20 tons per day during the uplift phase. 20 tons. That is the weight of 4 full-grown elephants worth of corrosive gas being released every 24 hours, day after day, week after week. To understand why this matters, you need to understand where sulfur dioxide comes from inside a volcano. The gas is created when magma deep underground releases dissolved sulfur as the pressure around it changes. As that magma rises, or as the surrounding rocks crack open new pathways, the gas escapes upward and eventually finds its way to the surface. A spike in sulfur dioxide emissions is one of the most reliable warning signs that a volcanic system is becoming more active. 2 days in May of 2024 stood out from the rest. On the 16th of that month, and again on the 28th, the fumaroles at Taftan released sudden bursts of gas that were strong enough to be detected from orbit. Local news outlets in Iran reported that residents of nearby villages saw plumes of smoke and ash drifting from the summit. Some described the smell of sulfur as overwhelming. Crops in nearby fields showed signs of damage from acidic gas exposure. These were not eruptions. They were what volcanologists call gas emission events, brief spikes during which the internal plumbing of the volcano released a pulse of pressure through its existing vents. Each event suggested that somewhere deep inside, new cracks were opening, new pathways were forming. The system was rearranging itself. The chemistry of the gas told another story. Taftan's emissions were rich in sulfur compounds, which is exactly the signature you would expect from magma that is fairly close to the surface. If the gas had come purely from a deep cooling reservoir miles below, the chemical mix would have been different. The actual mix pointed toward a fresh, shallow source. Either new magma had moved upward into the hydrothermal system, or the old hydrothermal system itself was being squeezed harder than it had been in millennia. Either way, the amount of sulfur dioxide pouring into the air had real consequences for the people living nearby. Sulfur dioxide is harsh on human lungs. It irritates the eyes and the throat. In high concentrations, it can cause severe breathing problems, especially for children, the elderly, and anyone with asthma. When it mixes with moisture in the air, it forms sulfuric acid, which falls back to the ground as a kind of acid rain that damages crops, contaminates water supplies, and corrodes metal. The wind in this part of Iran usually blows from the northwest, which means most of the gas drifts away from Kash. But weather patterns can shift, and when they do, the city would be directly downwind of the breath of a waking giant. The next mystery was what was actually pushing all that gas to the surface. When scientists try to figure out why a volcano is swelling, they think like detectives at a crime scene. Every clue points to a different culprit. The pattern of the uplift the location of the pressure source, the chemistry of the gas, the timing of the events. All of these have to fit together into a single coherent story. For Mount Taftan, the team identified two main suspects. Suspect number one is gas, specifically a buildup of trapped volcanic gases inside the shallow rocks beneath the summit. Volcanoes produce enormous amounts of gas as a normal part of their chemistry. Most of the time, that gas escapes through open pathways like the fumaroles at the top of the mountain, but sometimes those pathways get blocked. Mineral deposits crystallize inside the cracks, old fractures heal shut. The escape routes narrow. When that happens, gas accumulates. The pressure builds. Eventually, something has to give. This is what volcanologists mean when they talk about a sealed hydrothermal system. The hydrothermal system is the network of hot water, steam, and gas that sits in the rocks above the deep magma chamber. Think of it as a sponge made of stone, soaked with superheated fluids. Normally, the sponge leaks. When it stops leaking, it starts to stretch. If it stretches too far, it tears. The evidence for the gas theory at Taftan is strong. The pressure source is shallow, only 1,600 to 2,000 feet down. That is exactly the depth where you would expect the hydrothermal system to live. The chemistry of the emissions is right. The two big bursts of gas in May of 2024 fit the pattern of a sealed system suddenly finding new escape routes. Suspect number two is more dangerous. It is magma. Specifically, a small batch of fresh molten rock might have moved upward from the deep reservoir, intruded into the rocks above, and released its dissolved gases as the pressure around it dropped. The magma itself never reaches the surface. It cools quietly underground, but the gases it gives off as it ascends can dramatically pressurize the shallow rocks, causing exactly the kind of swelling and gas spikes that Taftan showed. This is called a magmatic intrusion. It is one of the most common precursors to a future eruption. Even a tiny intrusion, smaller than a single neighborhood block in volume, can be enough to shift the entire balance of pressure inside a volcano. And critically, magmatic intrusions are notoriously hard to detect from the outside. Without ground-based seismic monitoring, the moving magma is silent. The team could not definitively distinguish between the two suspects. The signal from orbit looks similar in both cases. A swelling summit, a burst of gas, a refusal to settle back down. To tell the difference, scientists would need instruments that simply do not exist on Taftan yet. Here is the unsettling part. Both scenarios are bad, but in different ways. If the cause is purely trapped gas, the most likely outcome is a phreatic explosion, a sudden steam blast at the surface. These events can be deadly within a few miles of the vent, but they rarely affect cities far away. They are also short-lived. A few hours, maybe a few days, and the system rebalances. If the cause is fresh magma, the situation is much more serious. A magmatic intrusion that succeeds in reaching the surface produces a full eruption. Lava flows, ash columns, pyroclastic flows, the kind of event that can change a region for decades. There is also a third possibility that the team has not ruled out. Both suspects could be working together. A small magmatic intrusion at depth could be feeding extra gas into a sealed hydrothermal system above it, building pressure on two fronts simultaneously. That would be the worst case of all. Without ground sensors, all the team can do is keep watching from orbit and wait for the next clue. That clue would come from a place no one expected. The fumaroles themselves. If you could stand at the summit of Mount Taftan on a quiet morning, the first thing you would notice is the sound. Not the roar you might expect from an active volcano, not the rumbling of an engine deep underground. What you would hear is hissing, a continuous, soft, almost peaceful hissing, like steam escaping from 100 kettles scattered across the broken rocks. That sound is coming from the fumaroles. They are the breath of the mountain made audible. Up close, each fumarole looks like a small wound in the earth, a crack in the volcanic rock, sometimes just a few inches wide, sometimes the size of a doorway. Around the edges of the opening, the rock is stained yellow and orange and white, painted by minerals carried up from below. Pure sulfur often crystallizes near the vents, forming brittle, lemon-colored crusts that crunch underfoot. The temperature inside these vents can range from a warm bath to nearly the boiling point of water, sometimes higher. Steam pours out continuously. So do other gases that you cannot see, including carbon dioxide and hydrogen sulfide. Standing too close, without protection, can be deadly. The gases displace oxygen from the air, and a curious hiker who leans in for a better look can lose consciousness in seconds. For the people who live in the villages around Taftan, the fumaroles have always been a part of life. Local shepherds know which valleys to avoid when the wind blows the wrong way. The smell of sulfur is a familiar warning, like the smell of smoke in a forest. It tells people to move uphill, into fresher air. What makes Taftan's fumaroles especially interesting to scientists is that they have been active for a very long time. There are written reports from the early 20th century describing steam and sulfur emissions from the summit. The 1902 records mention smoke that could be seen from miles away. In 1993, an unverified report described a small lava flow accompanied by intense fumarole activity. Even during the centuries when the volcano was officially considered extinct, the fumaroles kept hissing. This continuous activity is itself a clue. A truly dead volcano, one whose connection to the deep heat below has been completely severed, does not produce fumaroles. The chimneys go cold. The minerals stop forming. The vents seal up and disappear under erosion within a few thousand years. Taftan's fumaroles never sealed, which means the connection to the deep heat was never broken. The volcano was not extinct, it was just resting. During the uplift period of 2023 and 2024, the fumaroles changed in ways that the satellite team noticed. The total volume of gas being released increased. The temperature of the steam coming out of certain vents seemed to rise. New cracks opened in the summit area, and old cracks that had been quiet for years began to hiss again. Local guides who had climbed the mountain for decades reported that the smell of sulfur was stronger than they had ever experienced. These changes are exactly what you would expect if the underground pressure was searching for new escape routes. As the system gets squeezed, the gas finds the weakest paths through the rock. Old vents reactivate, new vents tear open. The mountain breathes harder. There is a phrase that volcanologists use to describe this kind of behavior. They call it precursor activity. It is the set of signals that a volcano gives off in the months and years before a major event. Not every precursor leads to an eruption. Many volcanoes show precursor activity and then quiet down again for decades. But every eruption in modern history has been preceded by precursors of some kind. Taftan was now showing precursors that it had never shown before, at least not within the memory of anyone alive. The next question was how shallow this pressure source really sat. The answer would change everything. When the team modeled the pressure source beneath Taftan's summit, the depth they calculated stunned them, maybe 2,000 feet at the deepest. That is roughly the height of a tall skyscraper, turned upside down and buried inside the mountain. To put that in perspective, the deep magma reservoir that feeds Taftan, the actual chamber where molten rock collects from below, sits more than 2 miles down, 11,000 feet, almost 7 times deeper than the source of the swelling. Whatever was pushing the summit upward was not coming from the deep belly of the volcano. It was coming from a chamber that sits right under the visitor's feet at the top. 1/2 mile of rock. That is the only thing standing between the trapped pressure and the open air. For comparison, when Mount St. Helens erupted in 1980, the magma that powered the blast had risen to a similar depth in the days before the explosion. When the volcano in Iceland called Grímsvötn erupted in 2011, the pressure source was at almost exactly this distance below the surface. Shallow pressure is what makes volcanic events sudden, explosive, and unpredictable. The reason has to do with how rock behaves under stress. Deep inside the Earth, the temperature is so high and the pressure is so enormous that rock flows almost like thick honey. When magma or gas pushes against deep rock, the surrounding material bends and gives way slowly. The result is a gradual, manageable release of pressure over months or years. Closer to the surface, the rock is cold and brittle. It does not flow, it cracks. When pressure builds against shallow, brittle rock, the rock holds and holds and holds until suddenly it breaks. The break is fast. Sometimes it is catastrophic. This is why phreatic explosions, the steam-driven blasts that come from sealed hydrothermal systems, can happen with almost no warning. The system builds pressure invisibly. The shallow rocks hold it back. Then a single fracture propagates through the cap, and the entire pressurized zone vents to the surface in a fraction of a second. The volume of the pressurized zone beneath Taftan's summit is hard to estimate exactly, but based on the size and shape of the surface bulge, the team calculated that the zone is large enough to produce a significant blast if it ever vented all at once. We are not talking about a planet-changing eruption. We are talking about something on the scale of the kind of explosion that can level a small town. There is one more wrinkle that makes this situation harder to read. The shallow pressure source is not connected directly to the deep magma reservoir. There is a layer of solid rock between them, several thousand feet thick, that acts like a barrier. As long as that barrier holds, the deep magma cannot feed new material into the shallow zone. The shallow zone is essentially isolated, like a sealed bubble. But barriers can fail. If a small intrusion of magma manages to crack through the solid layer, fresh molten rock can pour upward into the shallow zone and dramatically increase the pressure there. This is exactly what suspect number 2 from the previous chapter would look like in practice. A magmatic intrusion succeeding in breaching the cap rock. The team has no way of knowing whether this is happening right now. The radar satellites can only see the surface. They cannot see through the rock to watch the deeper layers move. What the satellites can see is whether the shallow pressure source continues to swell, hold steady, or begins to deflate. Each of those outcomes tells a different story. Swelling means the pressure is still building. Holding means the system has reached a kind of fragile balance. Deflating means the gas is finding ways out, either through the fumaroles or through some channel that the team has not yet detected. So far, the data suggests holding. The mountain has not risen significantly higher since May of 2024, but it has not gone down either. It is sitting in that fragile balance, pressurized and waiting. The next chapter takes us deeper to the magma chamber itself. 2 miles below the summit of Mount Taftan, in a region of rock so hot that ordinary stone behaves like soft clay, sits the heart of the volcano. This is the magma reservoir. It is the deep chamber where molten rock collects after rising from the much hotter mantle below. Geologists estimate that it sits somewhere between 3.5 and 9 kilometers below the surface, which translates to roughly 2 to 5.5 miles of solid earth above it. We have never seen it. No one has. No drill has ever reached it. No camera has ever recorded it. Everything we know about its size, shape, and contents comes from indirect measurements, seismic waves that bend as they pass through softer rock, gravity surveys that detect denser or lighter regions underground, chemical analysis of the gases that leak up from below. What those measurements tell us is that the reservoir at Taftan is real, it is hot, and it is still there. Most volcanoes that have been dormant for hundreds of thousands of years are assumed to have lost their reservoirs. The molten rock cools, it crystallizes, it turns into solid stone, indistinguishable from the surrounding crust. Without a liquid magma source, a volcano cannot erupt, period. It is geologically dead. But cooling takes a very long time. A magma reservoir the size of the one beneath Taftan, holding perhaps several cubic miles of molten rock, can take millions of years to fully solidify. During that time, the reservoir can be partially molten, partially crystalline, in a state that geologists call a mush. A mush is not a clean pool of liquid magma. It is a mixture, like wet sand, with crystals suspended in pockets of melt. A mush can sit dormant for enormous stretches of time. It can also be reactivated. If new heat or new magma is injected from below, the existing mush can begin to melt again, growing more liquid, more mobile, and eventually capable of feeding an eruption. The chemistry of the gases coming out of Taftan's fumaroles suggests that the reservoir below is still at least partially active. Sulfur compounds in particular point to the presence of fresh or reheated magma somewhere in the system. Pure cooling rock does not produce this kind of gas signature in significant quantities. This is the unsettling implication of the new measurements. Something at depth is still warm enough, still active enough, to push gas and possibly fluid upward into the shallow hydrothermal system. Whether that something is a reactivating mush, a small new intrusion of fresh magma from below, or simply leftover heat from an ancient cooling chamber, the team cannot yet say. There is also a second possibility that is harder to talk about. The deep reservoir might be doing something entirely new. Several recent studies have suggested that volcanoes once considered extinct can begin secretly accumulating fresh magma from below, slowly building up new reserves over tens of thousands of years. The Methana volcano in Greece is one example. Bolivia's Uturuncu is another, where ground deformation and seismic activity over recent decades have surprised researchers who thought the system was essentially finished. If Taftan is doing the same thing, the implications stretch far into the future. A volcano that is silently rebuilding its magma supply could, over the course of centuries, transform from a sleepy giant into an active threat. The current swelling might be the very first stage of a much larger awakening. Or it might be nothing more than a brief twitch, a momentary release of pressure that will fade as the system settles back into long quietude. The honest answer is that no one knows. Right now, this is firmly an unknown mystery rather than a confirmed fact. The data is too thin, the volcano too remote, the monitoring too sparse. What we do know is that the deep heat is still there, and the gas is still flowing, and the summit is still holding its new height. The next clue would come from a different angle entirely, the atmosphere above the mountain. In the spring of 2024, as Taftan's summit was finishing its swelling, two events occurred that the satellites picked up not as ground motion, but as plumes of gas in the sky. These events were the gas bursts of May 2024. The first happened on the 16th of the month, the second on the 28th. One lasted only a few hours. But during those hours, sulfur dioxide and steam poured out of the summit area in volumes far higher than the normal background emissions. To understand why this matters, you have to picture how volcanic gas behaves when it leaves the ground. Sulfur dioxide is denser than ordinary air. When it first comes out of a vent, it tends to hug the surface, flowing downhill like an invisible fog. As it warms in the sun and mixes with the wind, it rises into the atmosphere, where it can drift for hundreds of miles before falling back to the ground or being scrubbed out by rain. The bursts at Taftan rose high enough to be detected by satellites that monitor atmospheric chemistry from orbit. Instruments aboard a European Union satellite called Sentinel 5P, which measures gas concentrations across the entire planet, recorded clear spikes of sulfur dioxide above the volcano on both dates. The plumes were not large enough to be visible from space as a billowing cloud. They showed up as bright pixels on chemistry maps, brief flares of color against the otherwise quiet desert sky. For a volcano that had been considered extinct, even this was unusual. The pattern of the bursts told the team something important about what was happening underground. Both events came after the summit had stopped rising. That timing is consistent with a sealed hydrothermal system finally finding new escape paths. As pressure built during the inflation phase, the system was holding the gas in. When fractures opened in the caprock, the gas rushed out in pulses, each pulse corresponding to the failure of a different seal. This kind of behavior is sometimes called pressure pulsing. It is well documented at active volcanoes around the world. Mount Etna in Italy does it regularly. So does Kilauea in Hawaii. The difference is that those volcanoes are also producing lava and ash. Taftan is producing only gas, which means the magma itself, if there is any moving, is staying well below the surface. There is another reason the May 2024 bursts caught the team's attention. They marked the first time in modern records that Taftan had emitted detectable plumes. There is no other instance in the satellite era, no comparable event in the early 21st century, no previous flare in atmospheric records going back to the early days of orbital monitoring. The volcano had been chemically quiet for as long as humans had been looking, and then suddenly it was not. The local consequences were limited but real. Residents of villages downwind of the summit reported burning eyes, scratchy throats, and a thick rotten smell that lasted for hours. Some farmers complained that crops near the volcano showed yellowing leaves and stunted growth in the weeks after the bursts. Sulfur dioxide combined with atmospheric moisture produces sulfuric acid, a corrosive substance that damages plants, water, and metal. In larger eruptions, gas plumes can have global consequences. The 1991 eruption of Mount Pinatubo in the Philippines released so much sulfur dioxide into the upper atmosphere that it cooled the entire planet by about 0.5 degrees Fahrenheit for over a year. Even smaller eruptions, like Iceland's Eyjafjallajökull in 2010, can ground air traffic across continents for weeks. Taftan's bursts were nowhere near that scale. They were the equivalent of a small puff compared to those historic events. But they were a sign that the underground system was no longer in equilibrium. Something had changed. Something had cracked, and whatever had cracked was big enough to send measurable pulses of gas all the way to space. The team filed each burst into the growing dataset, alongside the radar measurements and the fumarole records. A picture was beginning to emerge. A picture of a volcano in the early stages of unrest, doing things it had not done in human memory. The next part of the story took the investigation in a completely unexpected direction. What happens when a volcano wakes up under a city? About 31 miles south of Mount Taftan, on a flat plain at the foot of the mountain range, sits the city of Kash. Kash is the second largest city in the Sistan and Baluchistan province. It is home to roughly 100,000 people. The population is mostly Baloch, an ethnic group with deep roots in the borderlands between Iran, Pakistan, and Afghanistan. The city sits at an elevation of around 4,500 feet in a region of mountains, dry valleys, and small farms. Most of the people who live in Kash have never thought of themselves as living near a volcano. Volcanoes are something that happens to other people, to Indonesians and Filipinos, to Italians and Icelanders. Iran has plenty of mountains, but its mountains are mostly dead, eroded, and stable. The idea that one of them could come back to life is not something that gets covered in school curriculums or local news. The mountain to the north has always been there. It has always smoked a little at the top. That is just how it is. That changed in the spring of 2024. Local journalists in Kash began publishing reports about strange smells, unusual smoke plumes from the summit, and a noticeable increase in the gas emissions that residents could see from a distance. Some described the smell of sulfur as becoming overwhelming on certain windy days. Others reported that visitors who hiked partway up the mountain came back complaining of headaches, dizziness, and burning eyes. When the Sentinel, one satellite data, was published later that year, the connection became obvious. The strange phenomena around Kash were not random. They were the early signs of a volcano waking up just 31 miles away. 31 miles is close, but it is not extremely close in volcanic terms. For comparison, the city of Naples in Italy sits only about 5 miles from Mount Vesuvius. Pompeii, the city famously buried in 79 AD, was even closer. In modern Indonesia, the city of Yogyakarta sits about 20 miles from Mount Merapi, which has erupted several times in recent decades. By those standards, Kash has a comfortable buffer. The buffer matters because most of the immediate hazards from a Taftan eruption would be limited to a smaller radius. Lava flows, if they happened, would not travel far enough to reach the city. The mountain is not steep enough for fast-moving pyroclastic flows to cover that much ground. Ashfall might dust the city, but it would not bury it. The bigger threat for Kash is something subtler: gas. Sulfur dioxide and other volcanic gases can drift on the wind for tens or even hundreds of miles. If a major gas release occurred at Taftan and the prevailing winds shifted southward, Kash would be directly downwind. The effects could include respiratory problems for vulnerable residents, contamination of water supplies through acid deposition, and damage to crops in the surrounding farmland. There is also the issue of infrastructure. Kash is connected to the rest of Iran by roads and a small regional airport. Volcanic ash, even in moderate amounts, can shut down road traffic and ground all flights. A few inches of ash can collapse roofs. A single eruption, even a relatively small one, could cut the city off from outside help for weeks. None of these scenarios are inevitable. They are not even particularly likely in the short term, but they are now possible in a way that they were not 5 years ago, when Taftan was still considered extinct. What troubles many researchers is that there is currently no formal evacuation plan, no early warning system, and no public education campaign for the residents of Kash regarding volcanic hazards. The local government has historically focused on earthquake risk, which is a much more frequent threat in the region. The idea that a long-dead volcano could suddenly become a public safety issue has not yet entered the mainstream conversation. Scientists in Iran and abroad have begun to advocate for changes. They want monitoring equipment installed on the mountain. They want gas sensors placed in Kash and surrounding villages. They want emergency drills, communication networks, and clear information available to the public about what to do if the volcano shows further signs of unrest. The political and logistical obstacles are significant, but the science is now beyond debate. Kash is a city in the shadow of a waking giant. The next chapter examines what would actually happen if that giant fully woke up. When most people imagine a volcanic eruption, they picture lava, glowing rivers of orange molten rock pouring down a mountainside, slowly burning everything in their path. This is the image from documentaries about Hawaii, from movies about Pompeii, from cartoons and storybooks. The truth is that lava is rarely the most dangerous part of an eruption. The most dangerous part, in many cases, is steam. This sounds absurd at first. Steam is the harmless white vapor that rises from a hot cup of tea. Steam is what you see coming out of a kettle on the stove. How could something so familiar and benign be a serious threat? The answer lies in pressure. When water is heated underground, surrounded on all sides by rock, it cannot expand the way it does in your kitchen. Instead, it gets superheated. Its temperature rises far above the normal boiling point of 212 degrees Fahrenheit. In the deep parts of a volcanic system, water can reach temperatures of 700 degrees or more while still remaining liquid, held in place by the enormous weight of the rocks above it. Now imagine that something disturbs that pressure. A new crack opens. A seal fails. The weight above the superheated water suddenly drops. In a fraction of a second, the liquid water flashes into vapor. When water flashes into steam, it expands by a factor of about 1600. 1 cubic foot of water becomes 1600 cubic feet of steam. If that expansion happens slowly, you get a kettle. If it happens in an instant, inside a mountain, you get an explosion. This kind of event is called a phreatic eruption. It is one of the most common types of volcanic event in the world, and one of the most lethal in terms of how quickly it strikes. Phreatic eruptions can happen with almost no warning. There may be a slight increase in surface temperature, a few extra rumblings of earthquake activity, a small uptick in gas emissions. But the actual blast itself can come within minutes of the final trigger. Hikers, climbers, and even scientists have died in phreatic eruptions because the warning time was simply too short to escape. In September of 2014, a volcano in central Japan called Mount Taftan erupted phreatically with no significant warning. The mountain had been considered safe enough that hundreds of hikers were on its slopes that day, many of them at the summit, enjoying the autumn views. Within minutes of the first explosion, 63 people were dead. Most were killed by hot rock and ash thrown out of the vent. Others were buried under thick deposits of debris. The eruption was relatively small by global standards, but it produced one of the deadliest volcanic disasters in modern Japanese history. The conditions at Mount Taftan are remarkably similar to the conditions at Ontake before its 2014 eruption. A pressurized hydrothermal system close to the surface, increased gas emissions, subtle but real ground deformation, a volcano that the public considered safe enough to be a hiking destination rather than a hazard. This is what worries the team studying Taftan most. Not a massive Pinatubo-style eruption, which would require fresh magma reaching the surface, and would almost certainly come with weeks or months of clear warning signs. The immediate concern is a phreatic blast, a sudden steam-driven explosion at the summit. That could happen within hours of any final trigger, and would kill anyone close enough to be hit by the debris. The radius of danger for a phreatic eruption is usually a few miles at most. That is small compared to the size of a city like Kash, but it is not small for the herders, hikers, and pilgrims who sometimes climb the mountain. It is not small for the workers at the small mining operations in the foothills. It is not small for anyone who happens to be on the slopes when the cap finally fails. Without ground sensors, without seismic monitoring, without a clear warning system, the people most at risk would have no idea what was about to happen. The mountain would simply explode. The blast would arrive before the news did. This is the kind of hazard that drives volcanologists to lose sleep, and it leads directly to the question of why this region is so poorly monitored in the first place. One of the strangest features of the swelling at Taftan is something the research team called triggerless behavior. In most volcanic systems, when the ground starts to lift, you can usually trace the cause to a specific event: a swarm of small earthquakes, a sudden shift in groundwater levels, a burst of magma rising from below. These triggers leave their fingerprints in the data, and skilled volcanologists can often identify the cause within days or weeks of the deformation beginning. At Taftan, no such fingerprint exists. The team checked rainfall records from the city of Kash, the closest place with reliable weather data. There had been no unusual precipitation during the months when the summit was rising. The local climate is dry. Total annual rainfall in this part of Iran is typically less than 8 inches per year. During the period of swelling, the totals were normal, perhaps even slightly below average. Rainfall could not be loading the rocks with new water and creating the pressure increase. They checked seismic catalogues covering a radius of more than 600 miles around the volcano. No earthquake of magnitude 5 or higher had occurred during the relevant period. Smaller earthquakes happened, as they always do in tectonically active regions, but none of them lined up in time with the start of the uplift. There was no quake that could have shaken loose a hidden chamber, no sudden fault movement that could have shifted the underground plumbing. They checked the broader pattern of volcanic activity in the region. No nearby volcanoes had erupted or shown unusual behavior during the swelling period. The Makran subduction zone had been moving at its usual creeping pace, with no sudden changes that could have transmitted stress to Taftan's roots. Everything external was normal, and yet the mountain was rising. This is what the team meant by triggerless. The unrest was not caused by something happening outside the volcano. It was caused by something happening inside the volcano. The system itself, of its own accord, had begun to change. The pattern of the rise was also unusual. Most volcanic deformation events follow a sharp curve. The ground rises rapidly at first, then slows, then either stabilizes or begins to fall back. Taftan's curve was different. The team described it as resembling a traveling wave. The uplift began slowly, accelerated to a peak rate of more than 4 inches per year, then gradually slowed and stopped. There was no sharp onset, no dramatic spike, no clear single event that started the process. Triggerless waves of deformation are difficult to interpret. In some cases, they reflect slow changes in the permeability of the rock. As fluids move through cracks underground, the cracks can become clogged with mineral deposits, gradually sealing the system. As the seals form, pressure builds. The ground rises in response to the gradual increase, not to any single cause. In other cases, triggerless deformation reflects something more concerning: the slow injection of new magma from below, in volumes too small and movements too subtle to register on the seismic instruments. Magma can migrate through the deep crust without producing detectable earthquakes if it moves slowly enough and through pre-existing pathways. By the time the surface begins to bulge, the new magma may already be in place, sitting in the shallow plumbing of the volcano, and waiting. The team could not distinguish definitively between these two scenarios. Both fit the available data. Both are theoretically plausible. What is clear is that whatever process started the swelling at Taftan came from inside the volcano itself. It was not woken up by an external shock. It was already changing on its own, in some slow and invisible way, until eventually the changes accumulated to the point where they became visible from orbit. This is one of the most unsettling aspects of the entire story. A volcano that has been silent for 700,000 years should not be capable of generating its own internal changes large enough to lift its summit by 3.5 inches. The fact that it did so, with no help from the outside world, suggests that the deep system is still alive in ways that no one had appreciated. The implications stretch beyond Taftan. They reach all the way back to the basic question of how we identify which volcanoes are dangerous and which are not. To understand why Taftan exists at all, you have to look at what is happening hundreds of miles below your feet, in a place no human will ever visit. The land beneath the Indian Ocean off the coast of southeastern Iran is part of a tectonic plate called the Arabian Plate. This is the same slab of crust that holds the entire Arabian Peninsula, including Saudi Arabia, Yemen, and Oman. The Arabian Plate is in slow but constant motion. It moves toward the north and east at a rate of roughly an inch per year, pushed by the spreading of the Red Sea. To the north, the Arabian Plate is colliding with the much larger Eurasian Plate. This collision is one of the most active tectonic boundaries in the world. It is what built the Zagros Mountains across western Iran. It is what creates the frequent earthquakes that shake Tehran and the surrounding regions. It is what powers the entire geological story of the Middle East. In most places along this boundary, the plates simply grind past or push against each other. In one specific zone, however, something different happens. The Arabian Plate dives beneath the Eurasian Plate, plunging downward into the hot mantle. This zone is called the Makran Subduction Zone, and it stretches along the coast of southern Iran and southwestern Pakistan for hundreds of miles. Subduction is one of the most powerful forces in geology. As the descending plate sinks into the mantle, it carries with it enormous quantities of water trapped in its rocks. The water, locked into mineral structures, gets squeezed out as the temperature and pressure rise during the descent. The released water then rises into the overlying mantle, where it acts like a chemical solvent, lowering the melting point of the surrounding rock. The result is magma, lots of it. This is the engine that has powered volcanoes for billions of years across the Pacific Rim, the Andes, the volcanic arcs of Indonesia and the Philippines, and dozens of other regions. Wherever you find a subduction zone, you find volcanoes lined up along the edge of the overlying plate, fed by magma generated by the sinking slab below. The Makran subduction zone follows this pattern, but with a twist. It is one of the slowest moving subduction zones in the world. The Arabian Plate is sinking at less than an inch per year, compared to several inches per year in places like Japan or Chile. This slow descent produces less magma. It generates fewer earthquakes. It builds fewer volcanoes. In the Makran region, only 3 volcanoes have formed along the entire arc. 2 of them, called Basman and Taftan, sit in southeastern Iran. The third, called Kowai Sultan, sits across the border in western Pakistan. All 3 are stratovolcanoes, the classic cone-shaped peaks that come from this kind of tectonic setting. Of the 3, only Taftan is currently considered active. The slowness of the Makran zone has historically made the region seem less dangerous than other subduction zones. Earthquakes are less frequent. Volcanic eruptions are rare. The entire arc has produced fewer disasters in recorded history than many other subduction systems. But slow does not mean inactive. The plate is still moving. Water is still being released. Magma is still being generated. It just happens at a pace so gradual that human civilization has rarely overlapped with the moments of release. The recent unrest at Taftan suggests that the engine is still running. Somewhere deep below the volcano, the subduction process is feeding heat and possibly fresh magma into the system. The 700,000 years of silence may have been a long pause between cycles, not a permanent shutdown. There is also a secondary concern. The Makran zone is capable of producing very large earthquakes, including tsunamigenic events that could affect the coast of Iran, Pakistan, India, and Oman. A magnitude 8 quake in 1945 generated a destructive tsunami that killed hundreds of people. A future quake of similar size could disturb the magmatic system at Taftan in ways that are hard to predict, potentially accelerating the volcano's awakening. The plates do not care about human timescales. They have been moving for tens of millions of years. They will keep moving long after we are gone. The question is whether we are paying enough attention to what they are doing right now. The next chapter focuses on a question that has haunted volcanology for over a century. What if our entire definition of an extinct volcano is wrong? There is a single number that decides whether the world treats a volcano as alive or dead. That number is 11,700 years. If a volcano has erupted at any point during the last 11,700 years, it is officially considered active or dormant. It gets monitored, mapped, and assigned hazard levels. It appears on emergency planning documents. Governments take it seriously. If a volcano has been silent for longer than 11,700 years, it is considered extinct. It usually gets dropped from monitoring lists. It rarely appears in hazard maps. Most national geological surveys do not bother tracking its activity. Tourists hike it. Hikers camp on its slopes. Children visit it on school field trips. The boundary line of 11,700 years is not random. It corresponds to the start of the Holocene era, the geological period that began at the end of the last ice age and continues to this day. The reasoning behind the rule was straightforward. If a volcano has not erupted during the entire span of human civilization, the odds that it will erupt in the immediate future seem low. The problem is that this rule was always a guess. It was based on the limited observational record of human history, not on any deep understanding of how magmatic systems behave over geological time. Volcanoes do not care about the calendar. They do not know that the Holocene started or that humans started building cities. They follow their own rhythms, dictated by the slow movements of magma and the slow accumulation of pressure deep underground. For most of the 20th century, the 11,700-year rule worked reasonably well. The volcanoes that caused major disasters were almost always volcanoes that had erupted at least once during the Holocene. The rule provided a useful filter for prioritizing limited monitoring resources. Geologists could focus on the volcanoes that had recently shown they were capable of activity and ignore the ones that seemed safely dead. In the 21st century, that rule has started to crack. The first major challenge came from a study published in early 2026 by researchers at ETH Zurich in Switzerland. The team mapped the geological history of a volcano in Greece called Methana, going back more than 700,000 years. They found that during Methana's longest period of dormancy, which lasted over 100,000 years, The volcano had continued to silently accumulate magma underground. The system was alive. It just was not erupting. If a volcano can store fresh magma for 100,000 years without showing any surface activity, then the 11,700-year rule misses an enormous amount of hidden risk. There could be hundreds of volcanoes around the world, currently classified as extinct, that are actually slowly building toward future eruptions. Mount Taftan fits this pattern perfectly. 700,000 years of silence, followed by sudden, measurable unrest. If the Mathana research is correct, the silence was not evidence of death, it was evidence of slow, hidden growth. A second challenge came from a volcano in Bolivia called Uturuncu. Uturuncu sits in the Andes Mountains and last erupted around 250,000 years ago. By the 11,700-year rule, it should be extinct. Yet, over the past several decades, satellite measurements have shown the entire region around the volcano slowly inflating. The ground has been rising at a rate of about half an inch per year over an area more than 40 miles wide. This kind of regional inflation is consistent with a large pool of magma slowly filling the deep reservoir below. Uturuncu, like Mathana, like Taftan, is not behaving the way an extinct volcano is supposed to behave. The pattern is becoming a trend rather than an exception. Volcanologists are now beginning to argue that the 11,700-year rule should be retired. In its place, they propose using direct measurements of magmatic activity, gas emissions, and ground deformation. To classify volcanoes, a volcano would be considered active if its system shows ongoing signs of life, regardless of how long ago its last eruption occurred. The implications are significant. Hundreds of volcanoes around the world would need to be reassessed. Many of them sit near population centers that have never thought of themselves as living near a volcanic hazard. The list of mountains that need monitoring would grow substantially. The cost of equipping all of them with sensors would be high, but the cost of leaving them unmonitored could be much higher. The next discovery shifts the focus from broad principles back to a specific, gripping question. What does the historical record actually say about Taftan? In the year 1902, in a remote corner of what was then called Persia, a strange thing happened on the side of a mountain. Local residents reported seeing smoke rising from the summit of Mount Taftan. Not just the usual wisps from the fumaroles, real smoke in volumes large enough to be visible from miles away. The reports made their way into a few European geographical journals of the time, written by colonial surveyors and travelers who happened to pass through the region. These reports were vague. They lacked the kind of detail that modern geologists need to confirm volcanic activity. There were no photographs, no instruments to measure gas emissions, no seismic stations to record any accompanying earthquakes. The reports were also written in a period when European scientists were not particularly interested in Persian geology, and they received almost no follow-up attention. Then the reports were largely forgotten. For most of the 20th century, the 1902 incident at Taftan was a footnote in obscure regional histories. When modern volcanologists began to compile global databases of volcanic activity in the second half of the century, the 1902 reports were sometimes included with a question mark next to them, sometimes left out entirely. The Smithsonian Institution's Global Volcanism Program, which maintains the most authoritative catalogue of volcanic activity in the world, lists Taftan's last possible eruption as occurring around the time of the 1902 incident, but with significant uncertainty. A second event in 1993 added another layer of mystery. According to local accounts and some unverified reports, a small lava flow appeared on the side of the volcano during that year. The flow, if it happened, was supposedly small and short-lived. There were no photographs that have surfaced in the scientific literature. No formal investigation took place at the time. The 1993 event is even more poorly documented than the 1902 incident, and it is regarded by most volcanologists today as essentially unconfirmed. This is the unsettling part of Taftan's story. The volcano may have been more active during the past century than the official extinct designation suggests. There may have been small eruptions, gas releases, or steam events that simply went undocumented because no one was watching closely. Compare this to a volcano like Mount St. Helens in Washington state. Before its catastrophic 1980 eruption, the volcano had been monitored continuously for decades. Every minor swarm of earthquakes was recorded. Every change in surface temperature was noted. When the volcano finally erupted, the warning signs had been visible for months, and the resulting evacuation saved thousands of lives. Now imagine if Mount St. Helens had been located in a remote region with no monitoring stations, no scientific interest, and a population that did not consider it a hazard. The 1980 eruption would have come with no warning at all. The death toll would have been catastrophic. This is essentially the situation at Taftan today. The mountain has shown signs of activity throughout the modern era, but those signs have been largely ignored. The recent satellite measurements are forcing a complete re-examination of the volcano's history, and the picture that is emerging is unsettling. There are also indirect hints in the geological record that Taftan may have been more active during prehistoric times than the 700,000-year figure suggests. The estimate of when the last major eruption occurred is based on dating of lava flows and ash deposits found around the volcano. These deposits give a clear signal for large eruptions, but smaller events, the kind that produce gas plumes and minor lava flows without depositing extensive layers of new material, can easily be missed. It is entirely possible that Taftan has had small, undetected eruptions throughout the past few thousand years. The 1902 incident may have been one of them. The 1993 event may have been another. The lack of documentation does not mean the events did not happen. It means that no one was looking when they did. The team studying Taftan today is now combing through old records, satellite imagery from earlier decades, and oral histories from local communities to piece together a more complete picture of the volcano's recent past. Early results suggest that Taftan has been more active than the official record indicates, although the evidence is still circumstantial. If those preliminary findings hold up, the 700,000-year silence may turn out to be a myth. The mountain may have been talking quietly all along. The world simply was not listening. The next chapter takes us to a different kind of disaster, one that struck a Japanese mountain with no warning at all. On a clear autumn morning in 2014, hundreds of hikers were climbing a mountain in central Japan called Ontake. It was a Saturday in late September, one of the most popular weekends of the year for Japanese mountaineering. The leaves were turning red and gold. The weather was perfect. The volcano had last erupted in a small, harmless steam event back in 2007. Before that, it had a minor eruption in 1979. Neither event had killed anyone. Local guidebooks listed Ontake as a moderate climb suitable for families with older children. Restaurants and souvenir shops dotted the trail. A weather station and emergency shelter sat near the summit. At 11:52 in the morning, the mountain exploded. There was no significant warning. Seismographs at nearby stations had recorded a small uptick in tremors during the previous month, but the increases had been so subtle that the official volcanic alert level had remained at 1 out of 5, the lowest possible setting. Hikers on the trail had no reason to suspect anything was wrong. The eruption was phreatic. Superheated water trapped in the shallow rocks beneath the summit had finally broken through its cap, flashing into steam in a fraction of a second. The expansion threw a column of ash, hot rocks, and gas thousands of feet into the air. Hot debris rained down across the upper slopes of the mountain. Some of the rocks were the size of bowling balls. 63 people died that day. Most were killed by the falling rocks. Some were buried by ash. A few were poisoned by the gas. Many of the bodies were not recovered until the following spring, after winter snows had melted and rescue teams could safely reach the upper slopes. The Ontake eruption was relatively small by volcanic standards. It produced no lava flow. It did not damage any villages below. The total volume of material ejected was tiny compared to events like Pinatubo or St. Helens. And yet it became the deadliest volcanic disaster in Japan in nearly 90 years, simply because the explosion happened in a place where people happened to be standing. The reason this matters for Mount Taftan is that the conditions at Ontake before its 2014 eruption were remarkably similar to the conditions at Taftan right now: a pressurized hydrothermal system close to the surface, increased gas emissions, subtle ground deformation, a volcano that the public considered safe enough to be a recreational destination rather than a hazard. Phreatic eruptions are notoriously difficult to predict. Unlike magmatic eruptions, which usually announce themselves with weeks or months of clear warning signs, phreatic blasts can occur with very little notice. The shallow rocks build pressure in silence. The gas accumulates. Then a single fracture propagates through the cap, and the whole pressurized zone vents to the surface in a moment. After the Ontake disaster, Japanese authorities significantly upgraded their monitoring of all the country's active and dormant volcanoes. New gas sensors, new tilt meters, new seismic stations. They also revised the criteria for issuing alerts, lowering the threshold for warnings about possible phreatic activity. The goal was to prevent another sudden disaster. Iran has not made similar investments. The Sistan and Baluchistan region remains one of the least monitored volcanic regions in the world. There are no real-time gas sensors at Taftan's summit, no tilt meters on its flanks, no permanent seismic stations within tens of miles of the volcano. If a phreatic eruption began at Taftan tomorrow, the first warning would likely be the explosion itself. This is the worst-case scenario that researchers like Pablo Gonzalez are trying to prevent. They are calling for international cooperation to install monitoring equipment on the volcano, even if it means working through diplomatic and logistical challenges that have nothing to do with science. Ontake is the cautionary tale. It is what happens when a sleeping volcano wakes up faster than the people watching it can respond. The next chapter brings the story home to a different kind of threat, the threat that drifts on the wind. In April of 2010, a volcano in Iceland with an almost unpronounceable name erupted. The volcano was called Eyjafjallajökull. By global standards, the eruption was modest. The lava flows were small. The death toll was 0. No villages were destroyed. And yet for 6 days, almost all air traffic across Europe came to a complete standstill. The reason was ash. Volcanic ash is not the soft, fluffy grey powder that comes out of a fireplace. It is composed of microscopic particles of pulverized rock and glass, sharp-edged and abrasive. When ash is sucked into the engine of a jet airliner at altitude, it can melt inside the hot combustion chamber and then re-solidify on the cool turbine blades, causing the engine to fail catastrophically. There have been documented cases of aircraft losing all 4 engines after flying through ash clouds, only restarting them after gliding to lower altitudes where the ash had dispersed. After the Eyjafjallajökull eruption, regulators across Europe banned all flights through airspace contaminated with significant ash concentrations. The result was the largest air travel shutdown since the Second World War. More than 100,000 flights were cancelled. 8 million passengers were stranded. The economic cost to the global economy was estimated at $5 billion. The volcano itself was not particularly violent. The eruption was rated a 4 on the Volcanic Explosivity Index, a logarithmic scale that runs from 0 to 8. Many eruptions throughout history have been larger. What made Eyjafjallajökull so disruptive was the combination of factors. The ash was lifted high into the upper atmosphere by an unusual eruption column. Persistent winds carried it south and east across Europe. The ash travelled for thousands of miles before finally dispersing. A future eruption at Mount Taftan could produce similar effects, depending on its size, the height of the ash column, and the prevailing winds at the time. The Middle East is home to some of the busiest air corridors in the world. Major hubs in Dubai, Doha, and Istanbul handle millions of passengers per year on flights connecting Europe with Asia. An ash cloud over the region could disrupt travel for weeks. The geography of the region also matters. Taftan sits roughly equidistant between the major airports of Dubai to the south, Tehran to the northwest, and Karachi to the east. Depending on wind patterns, ash from a significant eruption could potentially affect any or all of these aviation centers. The economic disruption would be enormous. There is also the question of ashfall on the ground. Even relatively small amounts of ash can collapse roofs, contaminate water supplies, damage electronics, and clog the air filters of vehicles. A few inches of ash fall in populated areas can cause public health crises lasting months. The good news is that ashfall is somewhat predictable once an eruption begins. Modern weather modeling combined with satellite monitoring of ash plumes can give cities downwind of an erupting volcano hours or even days of warning. Aircraft can be rerouted. Vulnerable populations can be evacuated. Agricultural and industrial operations can be shut down ahead of the falling ash. The bad news is that none of this monitoring infrastructure currently exists for Taftan. There is no formal system in place to detect an ash cloud rising from the volcano in real time. There is no agreement among regional aviation authorities about how to respond if such an event occurred. There is no public communication plan for residents of Kash or other downwind communities. These gaps are not technical problems, they are political and organizational problems. The technology to monitor a remote volcano like Taftan exists. Satellites already pass over the region multiple times per day. Modeling software can predict ash dispersal patterns with reasonable accuracy. What is missing is the institutional framework to translate raw data into actionable warnings. Building that framework would require cooperation among multiple national governments, international aviation authorities, and scientific organizations. Iran's political tensions with various Western countries make some forms of cooperation difficult. Sanctions, restrictions on technology transfers, and limitations on travel for foreign scientists all add complications. But volcanoes do not respect political borders. Ash clouds drift wherever the wind takes them. The same explosion that affects Iran could ground flights in Saudi Arabia, India, and beyond. Everyone in the region has a shared interest in monitoring this one mountain. The next chapter explores a much more local threat, what sulfur dioxide actually does to the human body when it drifts into a populated area. When sulfur dioxide reaches your lungs, it does not behave like ordinary air. The molecule is small. It dissolves quickly in moisture. The lining of your respiratory tract is wet by design, coated with mucus and fluid that protects the delicate tissues underneath. When sulfur dioxide gas hits that wet surface, it dissolves almost instantly, forming sulfuric acid right inside your airways. Sulfuric acid is one of the most corrosive substances in common use. It is the same chemical found in car batteries. At low concentrations, it irritates and inflames. At high concentrations, it eats through tissue. For people with asthma, sulfur dioxide can trigger severe attacks within minutes of exposure. Children, the elderly, and anyone with existing lung conditions are especially vulnerable. Even healthy adults can experience burning eyes, scratchy throats, coughing and chest tightness when concentrations rise above a few parts per million in the air. During the gas bursts at Mount Taftan in May of 2024, residents of villages downwind of the volcano reported exactly these symptoms. The sulfur dioxide cloud was not concentrated enough to cause mass casualties, but it was concentrated enough to make people sick, to send some to local clinics with breathing problems, and to leave others with sore throats and headaches that lasted for days. The effects on the environment were also significant. Sulfur dioxide combines with atmospheric water to form sulfuric acid droplets, which then fall back to the ground as a kind of acid rain. Acid rain damages crops by burning the leaves and lowering the pH of the soil. It contaminates surface water, killing fish and aquatic plants. It corrodes metal infrastructure, including bridges, vehicles, and irrigation equipment. Farmers in the foothills around Taftan reported yellowing leaves and stunted growth in some of their fields after the May 2024 events. The damage was localized and recoverable, but it was a preview of what could happen at much larger scale if a future eruption produced gas releases lasting weeks or months. There is also a longer-term risk that scientists are only beginning to fully understand. Continuous low-level exposure to volcanic gases over years can have cumulative health effects. Communities living near consistently active volcanoes show higher rates of respiratory disease, certain cancers, and cardiovascular problems compared to populations living in cleaner air. The exposure does not have to be dramatic to be dangerous over time. For the people of Kush and the smaller villages closer to Taftan, this raises a difficult question. How much of the volcano's recent activity is creating chronic health risks that have not yet been identified? Are residents already breathing more sulfur compounds than they realize? Are children growing up with subtle lung damage that will affect them for the rest of their lives? Without ground-based gas monitoring, these questions are impossible to answer. Satellites can detect large plumes of sulfur dioxide from orbit, but they cannot measure the kind of low-level, day-to-day exposure that affects human health on a chronic basis. To get those measurements, you need sensors on the ground, in the cities and villages where people actually live and breathe. This is one of the most urgent gaps in the current monitoring picture. Even if Taftan never has a major eruption, the gradual increase in gas emissions during the recent unrest period could be doing real harm to the people living downwind. They deserve to know what they are breathing. They deserve to know whether the volcano is making them sick. The cost of installing a network of gas sensors around the mountain would be modest, perhaps a few $100,000 for a basic system. The benefit would be the ability to track exposure in real time, warn vulnerable residents during gas bursts, and build a long-term record of environmental health in the region. So far, no such network exists. The people of Kash continue to breathe whatever the wind brings them, with no warning system, no protective measures, and no way to know what is in the air on any given day. The next part of the story moves from the local to the international, the proposal that scientists are now making to put eyes on this mountain. In the months after the Taftan study was published in 2025, Pablo Gonzalez and his team began making rounds at international conferences. They presented their findings to other volcanologists. They spoke with hazard assessment specialists. They argued, at every opportunity, that Mount Taftan needed urgent monitoring upgrades. The response was sympathetic but cautious. Almost everyone agreed that the volcano deserved more attention. Almost no one was willing to pay for it. The reasons were complicated. International scientific cooperation depends on diplomatic relationships, and Iran has historically had difficult relationships with many of the countries that lead in volcano monitoring technology. The United States Geological Survey, which operates one of the most advanced volcano observatories in the world, cannot easily install equipment in Iran due to long-standing sanctions and political tensions. European agencies have more flexibility, but they too face restrictions on certain technology transfers. Iran's own scientific community is interested, but underfunded. The country has talented geologists and engineers who would be capable of building a monitoring network. What they lack is the financial support, the high-end equipment, and the institutional backing needed to make such a project happen quickly. Geological monitoring is an expensive undertaking. A full network of seismometers, tilt meters, gas sensors, and data telemetry systems for a single volcano can cost several $1 million to install and hundreds of thousands per year to maintain. There is also the problem of physical access. Mount Taftan sits in a remote region with limited infrastructure. The roads near the volcano are rough. Electrical power is unreliable in many of the surrounding villages. Internet connectivity is spotty. Installing scientific instruments and keeping them running over long periods requires continuous logistical support, which is expensive in a region this isolated. The team has proposed a phased approach. The first phase would involve a small number of seismic stations placed at strategic points around the volcano, focused on detecting the kind of small earthquakes that often precede eruptions. The second phase would add gas sensors at the summit and in nearby villages, providing real-time measurements of sulfur dioxide and other volcanic gases. The third phase would integrate the data with satellite monitoring to create a comprehensive picture of the volcano's behavior. The total cost of this phased approach would be a fraction of what monitoring networks at well-watched volcanoes like Vesuvius or Mount St. Helens cost annually. Yet even this modest budget has been difficult to assemble. Some progress has been made. The European Space Agency has committed to maintaining regular satellite passes over the region, ensuring that the orbital data stream continues uninterrupted. A few academic partnerships have been formed between Iranian universities and research institutions in Europe and elsewhere. Limited training programs have allowed Iranian graduate students to learn advanced volcano monitoring techniques abroad. But the gap between what is being done and what should be done remains large. Taftan is still essentially watched only from orbit, and only by a small handful of researchers who have taken a personal interest in the mountain. If those researchers were to retire, change focus, or lose funding, the monitoring effort could collapse. The situation highlights a broader problem in global volcano monitoring. There are roughly 1,500 volcanoes considered potentially active worldwide. Of those, only a few hundred are well monitored. The remaining majority are watched sporadically, if at all. Many of them are in poor or politically unstable countries where local resources for monitoring are limited. When one of these poorly monitored volcanoes erupts, the consequences can be catastrophic. The 1985 eruption of Nevado del Ruiz in Colombia killed over 23,000 people, in large part because warning systems were inadequate. The 1991 eruption of Pinatubo in the Philippines was much better managed, but only because of extraordinary efforts by international scientific teams in the weeks before the explosion. Taftan could go either way. With proper monitoring, a future eruption could be predicted, evacuations could be ordered, and lives could be saved. Without monitoring, the volcano could surprise everyone, with consequences that would depend entirely on what kind of eruption occurred and where the wind was blowing that day. The next chapter takes a step back and looks at how unique Taftan really is, or whether mountains like it are quietly waking up everywhere. High in the Andes Mountains of southwestern Bolivia, more than 19,000 feet above sea level, sits a volcano called Uturuncu. Uturuncu's last eruption occurred roughly 250,000 years ago. By every conventional standard, it should be extinct. The volcano has been silent for far longer than the 11,700-year cutoff that defines the Holocene. There are no historical records of activity. The summit is glaciated, weathered, and quiet. And yet, for the past several decades, satellite measurements have shown something extraordinary happening beneath the entire Uturuncu region. The ground is rising. The uplift covers an area more than 40 miles wide. It is not concentrated at the summit of the volcano. It is spread across an enormous region, suggesting that something very large and very deep is changing underneath. The most likely explanation is that a massive pool of fresh magma is slowly accumulating in the deep crust, filling a reservoir that scientists call a magma body. The rate of inflation has averaged about half an inch per year over the past 2 decades. That sounds slow, but it adds up. Across 40 miles of ground, half an inch of vertical displacement represents a truly enormous volume of new material being injected into the crust below. Estimates suggest that the magma body beneath Uturuncu may be growing by hundreds of millions of cubic feet per year. If this trend continues for thousands of years, the result could be the formation of what geologists call a supervolcano. Supervolcanoes are not ordinary volcanoes that happen to be larger. They are a fundamentally different kind of eruption, capable of releasing enough material to bury continents in ash and trigger global climate changes lasting years. There have been no supervolcanic eruptions in human history. The last one occurred at Lake Toba in Indonesia, roughly 74,000 years ago, and it appears to have caused a near-extinction event for early humans, dramatically reducing global populations and altering climate patterns for millennia. The Yellowstone supervolcano in the United States is the most famous candidate for a future event, but its last major eruption was over 600,000 years ago, and the system shows no signs of imminent activity. Uturuncu is not currently an immediate threat. Even if the magma body is growing as quickly as the data suggests, it would still take tens of thousands of years to reach a size capable of producing a major eruption. The volcano is being watched closely, but no one is suggesting that evacuations are needed today. What Uturuncu represents is a category of volcano that does not fit the old framework. It is a system that should be dead by every conventional measurement, and yet it is clearly alive. Whatever rules previous generations of volcanologists used to classify mountains as extinct, those rules are missing something fundamental. The connection to Taftan is direct. Both volcanoes have been silent for hundreds of thousands of years. Both are showing measurable signs of unrest detected by satellite. Both are forcing scientists to reconsider basic assumptions about volcanic life and death. The two mountains are on opposite sides of the world, in completely different geological settings, and yet they are telling the same story. There are likely many more such volcanoes around the world currently classified as extinct that are quietly doing the same thing. Most of them have never been carefully measured. Most of them are in regions where ground-based monitoring is sparse or non-existent. The work that Gonzalez and his team did at Taftan, and that other teams have done at Uturuncu, is essentially proof of concept. The same techniques applied to other dormant volcanoes might reveal a global pattern of slow awakening. This possibility is what keeps senior volcanologists up at night. If even a small fraction of the world's supposedly extinct volcanoes are actually accumulating magma underground, the global hazard picture is much more complex than current emergency planning assumes. Cities that have been built confidently in the shadow of dead mountains might be living on borrowed time. It is an unsettling thought. The mountains are watching us. Some of them, slowly, are starting to move. The next chapter takes us to a Greek island where the same pattern played out hundreds of thousands of years ago, and what it might mean for the future. The Methana Peninsula juts out from the eastern coast of mainland Greece, a knob of land surrounded by the blue waters of the Saronic Gulf. From the right angle, you can see Athens in the distance, the white columns of the Acropolis catching the afternoon sun. The peninsula itself is dotted with small towns, tourist resorts, and the occasional ancient ruin. It is also a volcano. Methana is part of a chain of volcanic features called the South Aegean Volcanic Arc, a string of magmatic centers that runs across the southern Aegean Sea. The arc includes the famous island of Santorini, whose enormous eruption around 3,600 years ago may have helped destroy the ancient Minoan civilization. It also includes lesser-known volcanoes that have shaped the geological history of the region for millions of years. For most of recorded human history, Methana has been quiet. The volcano has produced more than 30 eruptions over the past several 100,000 years. But the most recent confirmed event happened around 2,250 years ago, recorded by the ancient Greek historian Strabo. Since then, the system has been almost entirely silent, with only occasional small earthquake swarms reminding the locals that the mountain still exists. In 2026, a team of researchers at ETH Zurich in Switzerland published a study that changed how scientists think about volcanoes like Methana. The team analyzed rock samples from 31 locations across the volcano, looking for tiny mineral crystals called zircons that can be precisely dated using radioactive decay. What the team found was startling. During Methana's longest dormant period, a stretch of more than 100,000 years of silence, the volcano had been actively producing new zircon crystals underground. Zircons form in environments where magma is cooling and crystallizing. The presence of new zircons during the supposedly quiet period meant that magma had been brewing beneath Methana the entire time. even though no eruptions had reached the surface. The implications are profound. Mount, a volcano that everyone considered safely dormant for over 100,000 years, had actually been alive the whole time. The system was just storing its activity below ground, rather than venting it to the surface. The senior author of the study, a volcanologist named Olivier Bachmann, described the findings as a wake-up call. Volcanoes can breathe underground for millennia without ever breaking the surface. The longer they breathe in silence, the more pressure they can store, and the larger their eventual eruption can be. Long quiescence does not mean death. In some cases, it may mean that the system is loading itself for a much bigger event. This is exactly the framework that helps explain what is happening at Taftan. If Mount can store magma silently for 100,000 years, then a volcano like Taftan, silent for 700,000 years, could be holding extraordinary amounts of pressure beneath its surface. The recent unrest may not be the system fading away. It may be the system finally finding a way to release something that has been building for an unimaginably long time. The Mount research also points to something that emergency planners and government officials struggle to handle. Volcanic time is not human time. A volcano that has been silent for 100,000 years is, by any human measure, dead. Civilizations have risen and fallen in that time. Languages have evolved, continents have changed. To call such a system alive feels almost paradoxical, and yet the chemistry, the physics, and the geology all say that it is alive. The mountain is just running on a different clock. For the people who live near volcanoes like Mount and Taftan, this creates a difficult psychological situation. The threat is real, but it is also distant in a way that the human mind has trouble processing. Most people cannot maintain a sense of urgency about a hazard that might or might not become acute over the next decade or century. We are wired to respond to immediate dangers, not to slow accumulations of underground pressure. The challenge for scientists and policymakers is to communicate the reality of these long-cycle threats without either understating the danger or causing panic. So far, the world has not figured out how to do this very well. Most discussions of volcanic risk focus on the immediate, the dramatic, the obvious. The slow, hidden build-ups beneath places like Mount and Taftan get less attention than they deserve. The next chapter shifts to a much more recent example. A volcano that gave warnings was watched, and ultimately erupted with consequences that changed the global climate. In April of 1991, a mountain in the Philippines that almost no one had heard of began to rumble. Mount Pinatubo had been quiet for over 500 years. Most of the residents of the surrounding region did not even know they were living near a volcano. The mountain was covered in dense jungle, home to indigenous communities who farmed the slopes and gathered fruit from the forests. To outside eyes, it looked like just another peak in a country full of beautiful peaks. But underneath, the system was waking up. The first signs were small earthquakes beginning in March of 1991. The tremors were too weak to be felt by most residents, but seismic stations operated by the Philippine Institute of Volcanology and Seismology picked them up clearly. Over the next several weeks, the earthquakes increased in frequency and intensity. New cracks opened on the volcano. Steam began rising from vents that had been quiet for centuries. The Philippine government, working with American volcanologists from the United States Geological Survey, launched one of the most aggressive volcano monitoring efforts in history. Instruments were installed across the mountain. Hazard maps were drawn. Evacuation plans were developed for the towns and military bases in the volcano's potential blast zone. The decision to evacuate, when it finally came in early June, was contentious. More than 200,000 people had to be moved from their homes. 2 American military bases, Clark Air Base and Subic Bay Naval Station, had to be partially abandoned. The economic cost was enormous. There were no guarantees that an eruption was actually coming. It came on June 15, 1991. The eruption was one of the largest of the 20th century, ejecting more than 10 cubic kilometers of material into the atmosphere. Ash fell across hundreds of square miles, Pyroclastic flows raced down the mountainsides at hurricane speeds. The eruption was rated a 6 on the Volcanic Explosivity Index, in the same category as the famous Krakatoa eruption of 1883. And yet the death toll was relatively low. Approximately 800 people died, mostly from collapsed roofs caused by ash mixed with water from a passing typhoon. By comparison, the Mount Pelée eruption in 1902, which had a similar explosive force, killed 30,000 people in a matter of minutes. The Krakatoa eruption killed over 36,000. The difference at Pinatubo was that the warning systems worked. People got out in time. The lessons from Pinatubo applied directly to Taftan. The Philippines volcano showed that even a long-dormant system, with no recent history of activity, can produce a catastrophic eruption with relatively short warning. It also showed that effective monitoring, combined with the political will to act on warnings, can save tens of thousands of lives. The differences between Pinatubo in 1991 and Taftan in 2026 are also worth noting. Pinatubo had a robust scientific monitoring network in place by the time the eruption began, thanks to the rapid response of Philippine and American authorities. Taftan has almost none. Pinatubo was located in a region with established emergency management infrastructure. Taftan is in one of Iran's most underserved provinces. Pinatubo had clear cooperation between national governments and international scientific bodies. Taftan does not. If Taftan were to follow a Pinatubo-style trajectory, with months of escalating unrest leading to a major eruption, the current system would likely fail to provide adequate warning. The satellite monitoring that exists today would catch the broad outlines of the buildup, but the precise timing and location of the eruption would be much harder to predict without ground-based instruments. This is what makes the comparison both informative and worrying. We have the proof that monitoring works. The Pinatubo evacuation saved many lives. The infrastructure to do similar work at other volcanoes exists. What is missing at Taftan is not the science, it is the will and the resources to apply the science. There is also a global dimension to consider. The Pinatubo eruption ejected so much sulfur dioxide into the upper atmosphere that it cooled the entire planet by about 0.5 degree Fahrenheit for over a year. Crops failed in some regions, weather patterns shifted. The cooling effect was measurable in temperature records around the world. A future eruption at Taftan, if it were large enough, could produce similar global effects. The probability of such an event is low, but it is not zero, and the consequences, if it happened, would extend far beyond Iran or the Middle East. The next chapter explores what happens when a phreatic blast goes wrong, and the chilling speed at which one can develop. Phreatic eruptions happen faster than the human brain can process. When the cap rock above a pressurized hydrothermal system finally fails, the transition from normal conditions to violent explosion can occur in less than a single second. The superheated water trapped underground flashes into steam almost instantaneously. The expansion is extreme. The same volume of liquid water becomes roughly 1,600 times more volume of vapor. Inside the confined space of an underground chamber, that expansion has nowhere to go but up. The steam blasts through any remaining rock above it, throwing fragments of the cap into the air at speeds that can exceed the speed of sound. Hot water that did not have time to vaporize in the initial flash gets carried along with the explosion, scalding everything in its path. Ash, pulverized by the violent fragmentation of the cap rock, fills the air with abrasive particles. A person standing on the slope of the volcano during a phreatic blast has very little chance of survival. The shockwave alone can knock someone unconscious within hundreds of feet of the vent. Falling rocks, some of them large enough to crush a car, rain down across an area that can be a mile or more wide. The hot ash and steam can cause severe burns at distances of 0.5 mile or more from the source. The Mount Taftan disaster in 2014 demonstrated this brutal reality. Hikers near the summit reported almost no warning before the explosion began. One survivor described the eruption as starting with a single loud crack, followed by complete chaos. Within seconds, the air was filled with hot rock and ash. Visibility dropped to zero. People who tried to run were knocked down by the falling debris. Many of those who died were killed almost instantly by direct impact. The difference between a phreatic eruption and a magmatic eruption is critical for understanding the threat. Magmatic eruptions, the kind that produce lava flows and large ash columns, almost always announce themselves with weeks or months of escalating warning signs. The magma rising through the crust generates earthquakes, gas emissions, and ground deformation that careful monitoring can detect well in advance. A magmatic eruption gives evacuation planners time. Phreatic eruptions do not. The warning signs for a steam-driven blast can be extremely subtle. A small increase in surface temperature, a slight change in gas chemistry, a tiny uptick in tremor activity. Even with state-of-the-art monitoring, predicting the precise timing of a phreatic eruption is one of the hardest challenges in volcanology. Without monitoring, predicting it is essentially impossible. This is why the situation at Mount Taftan is so concerning. The volcano's current unrest has all the hallmarks of a system that could produce a phreatic eruption. The pressurized zone is shallow. The hydrothermal system is active. The gas emissions have spiked. If the system finally cracks, the blast could come with little or no warning. The hazard radius for a phreatic eruption at Taftan would likely be a few miles around the summit. That is small enough that the city of Kash, 31 miles away, would not be in immediate danger, but anyone closer than that would be at serious risk. Climbers, herders, miners, scientists, anyone who happened to be on the slopes of the mountain during the blast. There is also a secondary hazard from a phreatic event that extends much further. The plume of gas and ash thrown into the atmosphere by even a small steam blast can drift for hundreds of miles, carrying corrosive sulfur compounds and abrasive particles into populated regions. Small phreatic events at various volcanoes around the world have caused widespread health problems and infrastructure damage, despite producing no lava flows or pyroclastic flows. For Taftan, the most realistic short-term scenario is that the volcano experiences one or more phreatic eruptions over the coming years or decades, possibly without producing a major magmatic event. These steam blasts could be moderate in size, dangerous to anyone nearby, but not catastrophic on a regional scale. The bigger question is whether such events would represent the end of the current unrest cycle, or merely a step towards something larger. Historical patterns at other volcanoes suggest that phreatic eruptions can sometimes be precursors to magmatic activity. The Mount St. Helens eruption of 1980 was preceded by months of phreatic events. The Pinatubo eruption included phreatic phases in its early weeks. If Taftan follows similar patterns, a steam blast might be the warning that something larger is on the way. The next chapter examines a different kind of warning: the signals that volcanoes give off before they erupt, and what scientists are doing to read them. Volcanoes do not erupt without warning. They almost always give signs, sometimes for years before the actual event. The challenge for scientists is learning to read those signs and distinguish real precursors from background noise. The most reliable warning signs fall into a few main categories. Earthquakes are usually the first indicator. As magma moves through the crust, it cracks rocks and creates small tremors. Most volcanic earthquakes are too weak to be felt by humans, registering only on sensitive seismographs. But the patterns they form can reveal a great deal about what is happening underground. Swarms of small quakes at increasing depths can indicate magma rising. Long-period tremors with characteristic low-frequency signatures can reveal the movement of fluids through cracks. Ground deformation is the second major indicator. As magma or pressure builds beneath the surface, the ground above bulges, tilts, or shifts. These changes can be measured with instruments on the ground or with satellites in orbit. The Mount St. Helens eruption was preceded by a famous bulge on the north side of the mountain, growing visibly larger over weeks. The recent activity at Taftan is itself a deformation signal. Gas emissions are the third critical indicator. Magma releases dissolved gases as it rises, and changes in the volume or composition of those gases can indicate what is happening below. A spike in sulfur dioxide, in particular, often signals fresh magma close to the surface. Carbon dioxide ratios, helium isotopes, and other chemical signatures can also reveal subtle shifts in the volcanic system. Surface temperature changes are a fourth indicator, though usually a less reliable one. As magma rises, it can heat the rocks around it, sometimes producing detectable warming at the surface. Thermal infrared satellites can monitor these changes from orbit, providing a fourth line of evidence about volcanic activity. At Taftan, 3 of these 4 indicators have shown clear signals during the recent unrest. The ground has deformed, the gas emissions have increased. There have been reports of warmer temperatures at the summit. Only the seismic signal is missing, and that absence is largely a result of the lack of ground-based instruments, rather than an indication that no earthquakes are occurring. The ideal scenario for monitoring a volcano like Taftan would integrate all 4 indicators in real time. Seismographs would detect every small tremor and identify its location. Tilt meters and GPS stations would track ground deformation continuously. Gas sensors would measure emissions as they happen. Thermal cameras would watch the summit for heating events. All of these data streams would feed into a central monitoring system, where scientists could analyze the combined signal and issue warnings as appropriate. This is the kind of system that watches volcanoes like Etna in Italy, Kilauea in Hawaii, and Vesuvius in southern Italy. Each of these mountains has hundreds of instruments providing continuous data, and teams of scientists who work in shifts to interpret the information 24 hours a day. The result is one of the safest volcanic environments in the world. Even when these mountains erupt, the warnings are usually accurate enough to save lives. Taftan has nothing like this. The mountain is being monitored almost entirely from orbit, with delays of hours or days between data acquisition and analysis. Any sudden change at the volcano would be invisible to the current system until satellites passed overhead and the resulting images were processed. There is a path forward. Modern volcano monitoring equipment is more affordable and easier to install than ever before. Solar-powered sensors with satellite data uplinks can operate in remote locations with minimal maintenance. International scientific collaborations have developed standardized protocols that make it possible to set up monitoring networks relatively quickly when the will exists. The question for Taftan is whether that will exists. The international scientific community has expressed interest in supporting monitoring efforts. Iranian scientists are eager to participate. The technology is available. What is needed is the political and financial commitment to actually make it happen. In the meantime, the satellites continue to pass overhead, and the team continues to watch. The volcano is sitting in its strange equilibrium, neither rising nor falling, holding its pressurized state through the seasons. The next chapter goes back into the geological deep past to understand what has happened at Taftan before, and what those events suggest about what could happen next. Every volcano carries its history in the rocks around it. Each eruption leaves behind a layer of cooled lava, a deposit of ash, or a band of pumice that settles to the ground and hardens. By reading these layers, geologists can reconstruct what the volcano has done in the past, and sometimes infer what it might do in the future. At Mount Taftan, the geological record is fragmentary but informative. The most prominent feature of the volcano's recent geological history is its summit cone. This cone is composed of relatively young volcanic rocks, formed during a series of eruptions that occurred over the past several million years. The most recent of these large eruptions, the one that produced the current shape of the cone, happened roughly 700,000 years ago. This is the 700,000-year figure that gets cited so often in news coverage of the volcano. But the cone is not the entire story. Around the base of the volcano, geologists have identified older layers of volcanic material that date back several million years. These older layers indicate that the Taftan system has been active off and on for a very long time. The current cone represents only the most recent phase of a much longer history. The chemistry of the rocks at Taftan tells another part of the story. The lavas are predominantly andesitic, a type of volcanic rock common at subduction zone volcanoes. Andesitic eruptions tend to be more explosive than the runny basaltic eruptions you see in Hawaii, but less catastrophic than the rhyolitic eruptions of supervolcanoes. They can produce significant pyroclastic flows, ash columns, and blast events, but they typically do not generate the kind of region-altering catastrophes associated with the largest eruptions in geological history. The volume of material erupted by Taftan during its known history is moderate. Estimates suggest that the entire volcano has produced perhaps a few cubic kilometers of erupted material over the past million years. By comparison, the 1991 Pinatubo eruption alone produced more than 10 cubic kilometers in a matter of days. So Taftan's overall productivity is on the lower end of the spectrum for stratovolcanoes of its size. This relatively modest output is what has historically led many geologists to consider Taftan a low-priority volcano. The rocks suggested a system that, even when active, produced only moderate eruptions. The long, quiet period of the past 700 years reinforced the impression that the system was winding down. The recent satellite data is now forcing a reassessment. If the system is still active enough to produce measurable ground deformation today, then the historical pattern of moderate output may not be a reliable guide to the future. Volcanoes can change their behavior over geological time. A system that produced small eruptions in the past can sometimes produce much larger ones if conditions in the deep crust change. There is also the question of what kind of eruption would actually occur if Taftan finally vented in a major way. Based on the chemistry of the existing rocks and the structure of the current pressurized zone, the most likely scenario for a future eruption would be a moderate explosive event. Pyroclastic flows could race down the mountainsides for several miles. Ash would fall over a wide area downwind. Gas emissions would increase dramatically. The local consequences would be severe, but probably not regional in scope. A worse scenario, though less likely, would involve the deeper magma reservoir feeding new material into the shallow system. If a substantial volume of fresh magma reached the surface, the eruption could be much larger, potentially affecting populations across the wider region. The probability of this kind of major event in the near term is considered low, but it is not negligible. The geological record also reveals something useful about the timescales involved. Major eruptions at Taftan in the past appear to have been separated by tens of thousands or even hundreds of thousands of years. The interval between major events is much longer than the interval between minor events, like the gas bursts of May 2024. So the most likely course of the current unrest is a series of smaller events over many decades, rather than a single climactic eruption in the immediate future. But likely is not certain. The system is showing behaviors that have not been observed in human history. The rocks can only tell us so much. The next chapter looks at one of the strangest features of the recent unrest, and what it might mean for the deep system. 18 months after Mount Taftan's summit stopped rising, the ground at the peak is still holding its new height. This is one of the most puzzling features of the entire episode. In the typical pattern of volcanic ground deformation, an inflation event is followed by a deflation event. The pressure that lifted the surface eventually finds a way out, either through eruption, through gas release, or through gradual seepage into surrounding rocks. The ground sinks back down, sometimes to its original level, sometimes to a slightly higher position that reflects permanent changes in the volcanic system. Taftan has not deflated. The summit area remains lifted by the same 3.5 inches it gained during the swelling phase of 2023 and 2024. There has been no measurable decrease in elevation in the months since the rise stopped. The pressure that pushed the mountain upward is, by all available evidence, still trapped underground. This frozen state is unusual. It suggests that the pressurized zone beneath the summit has reached a kind of mechanical equilibrium, where the forces pushing outward are balanced by the strength of the surrounding rock. The system is loaded but stable. It is holding. There are two main possibilities for what could happen next. The first possibility is that the system slowly leaks. Over months or years, the trapped pressure could find subtle ways to escape, through cracks too small to be detected from orbit, through gradual diffusion into surrounding pore spaces, through slow chemical reactions that absorb some of the gas. If this happens, the ground might gradually subside back toward its original level, and the unrest episode would end without further drama. The volcano would return to its long sleep. The second possibility is that the system continues to load. New material, whether gas or magma, could be slowly added to the pressurized zone from below, increasing the pressure further over time. If this happens, the ground might begin to rise again, possibly faster than during the original inflation phase. Eventually, the pressure would exceed the strength of the cap rock, and the system would fail in either a phreatic explosion or a magmatic eruption. There is also a third possibility that combines elements of both. The system could oscillate, with periods of loading followed by periods of partial release, building up over time toward an eventual major event. This is the pattern that has been observed at some volcanoes during the years before significant eruptions. The ground rises and falls in cycles, each cycle adding a small amount of net pressure to the system, until finally the cumulative load exceeds the rock's ability to contain it. Which scenario is unfolding at Taftan right now is impossible to say with certainty. The satellite data shows the ground holding steady, but it cannot reveal what is happening at depth. Without ground-based seismic monitoring, the team cannot detect the small tremors that would indicate fluids continuing to move through the system. Without continuous gas measurements, they cannot tell whether emissions are slowly increasing or holding constant. What can be said is that the current frozen state is not necessarily safe. A system that has been loaded with pressure and is currently in equilibrium can fail at any time. The trigger for failure might be an external event, such as a regional earthquake. It might be an internal event, such as a small chemical reaction that weakens a section of cap rock. It might be no obvious event at all, just the slow accumulation of stress finally exceeding a threshold. This uncertainty is what makes long-term forecasting at Taftan so difficult. The volcano could remain in its current state for decades, with no further developments. It could suddenly produce a phreatic eruption next month. It could begin a slow build-up toward a much larger event years from now. All of these outcomes are consistent with the available data. For people who live near the volcano, this kind of uncertainty is psychologically taxing. The threat is real, but indefinite. The danger could materialize tomorrow or never. There is no clear point at which residents can declare the situation resolved and return to normal life. They live, in effect, in a state of permanent low-grade alert. For the international scientific community, the situation at Taftan represents both a research opportunity and an ethical challenge. The volcano is an ideal natural laboratory for studying long-term unrest at long-dormant systems. But the people who live nearby deserve more than research interest. They deserve protective action, public communication, and the basic infrastructure of monitoring that other vulnerable communities take for granted. The next chapter looks at how this kind of long-term hazard fits into the broader pattern of volcanic risk worldwide. The world has roughly 1,500 volcanoes that are considered potentially active. Of those, only a few hundred are equipped with comprehensive monitoring systems. The rest are watched sporadically, irregularly, or not at all. This monitoring gap is one of the most underappreciated risks in modern hazard assessment. The volcanoes that get the most attention are the ones that have erupted recently or that sit near major population centers. Vesuvius near Naples, Etna in Sicily, Mount St. Helens in Washington state, Sakurajima in southern Japan. These are the famous mountains, the ones that make the news when they rumble, the ones with permanent observatories and dedicated scientific teams. Below this top tier sits a much larger group of volcanoes that get sporadic attention. They might have a few seismic stations and occasional satellite analyses, but they lack continuous comprehensive monitoring. These are the volcanoes that have erupted within the past few thousand years, but not within recent memory. There are several hundred of them around the world, scattered across the major volcanic regions of the planet. Below that tier sits the largest group of all, the volcanoes that have not erupted within the Holocene era and are therefore considered extinct. There are thousands of these mountains around the world. Most of them receive almost no scientific attention. Many of them have not been visited by geologists in decades. Their hazard potential has often not been assessed at all. Mount Taftan was, until recently, in this third tier. Researchers in the field of volcanology had heard of it, but the volcano was not on any active monitoring lists. The reason it received attention in 2024 was almost accidental. A doctoral student happened to look at satellite imagery of a remote region. A signal happened to appear that warranted further investigation. A research team happened to have the expertise to analyze the data carefully. If those things had not lined up, the unrest at Taftan might have continued for years or decades without anyone noticing. The mountain would have kept rising. The gas would have kept venting. Eventually, perhaps, an eruption would have caught the world by surprise. This pattern of accidental discovery is not unique to Taftan. Several other long-dormant volcanoes have been identified as potentially active in recent years, often through similar processes of routine satellite monitoring, catching unexpected signals. The Bolivian volcano Uturunco was discovered to be inflating in the 1990s, almost by accident, when researchers were looking at radar data for unrelated purposes. A volcano in the Caribbean called Sulfur Hills had been considered dormant until it began erupting in 1995, at which point it became clear that the system had been active in subtle ways for some time. Each of these discoveries has the same implication. The world has been substantially underestimating the number of volcanoes that pose real hazards. The list of mountains that need monitoring is much longer than current programs assume. The reason this matters extends beyond science. Many of the volcanoes that fall into the underexamined category are located near population centers that have grown substantially in recent decades. A volcano that was harmlessly remote 100 years ago might now sit near a major city, an industrial complex, or a critical transportation corridor. The hazard level of the volcano has not changed, but the consequences of an eruption have grown enormously. Iran is a good example. The country has experienced rapid urbanization over the past century. Cities like Tehran, Mashhad, Esfahan, and Shiraz have grown into massive metropolitan areas, in some cases multiplying their populations by factors of 10 or more. The infrastructure supporting these cities, the highways, airports, power grids, water systems, all have to function reliably for millions of people to maintain modern lifestyles. A major eruption in even a remote part of the country could disrupt this infrastructure in ways that would cascade through the entire economy. Kash itself, while small by Iranian standards, has tripled in population over the past 50 years. The agricultural region around Mount Taftan supports hundreds of thousands of people who depend on local crops and livestock. A significant eruption would affect these communities directly in ways that did not exist when the volcano was last active. The implication is that hazard assessment cannot remain static. As populations grow and infrastructure expands, the risk profiles of supposedly dormant volcanoes need to be continuously updated. A mountain that was safe to ignore in 1925 might be dangerous to ignore in 2025. The science has to keep up with the changing human geography around it. So far, this kind of dynamic hazard assessment is not happening systematically for most of the world's under-examined volcanoes. Resources are limited. Political will is sporadic. The volcanoes that get attention are the ones that announce themselves, while the silent ones remain in the shadows. The next chapter takes us to a chilling possibility about what those silent ones might be hiding. Around the planet, in regions as varied as the deserts of Iran, the mountains of Bolivia, the islands of Greece, and the highlands of Central Africa, sit volcanoes that the world has officially declared dead. Most of them are dead. Most of these mountains have indeed lost their connection to deep heat, their magma reservoirs cooled into solid rock, their plumbing systems sealed forever by time and erosion. They are not coming back. But some of them are not dead. Some of them are merely quiet, with magma still brewing beneath the surface, with pressure slowly accumulating in hidden chambers, with the potential to wake up at any time over the coming centuries. The challenge for science is figuring out which is which. Until recently, this distinction was made primarily through the 11,700-year rule discussed earlier in this video. If a volcano had erupted within the past 11,700 years, it was active or dormant. If not, it was extinct. The rule was simple, easy to apply, and broadly useful for prioritizing limited resources. The recent discoveries at Mathama, Uturumqu, and Taftan are forcing scientists to abandon the simple rule and develop more sophisticated criteria. The new approach focuses on direct measurements of system activity rather than on time since last eruption. A volcano is now considered potentially active if it shows ongoing signs of life, regardless of how long it has been since the most recent eruption. The signs of life can include any of the following: continuous gas emissions from fumaroles or hot springs, indicating that heat and chemistry are still active underground; measurable ground deformation, even if subtle, suggesting that pressure or volume changes are occurring at depth; seismic activity, including small earthquakes or long-period tremors that indicate fluid movement; anomalous heat at the surface, detectable by infrared satellites; chemical signatures in nearby groundwater or soil that indicate volcanic gases are diffusing through the system. When these criteria are applied systematically, the list of potentially active volcanoes around the world grows substantially. Estimates vary, but some researchers suggest that the true number of volcanoes that deserve close monitoring might be twice or 3 times the current official total. This is a sobering possibility. It means that hundreds or thousands of mountains, currently classified as extinct and largely unmonitored, might be quietly active in ways that have not been recognized. Many of them sit near populated areas. Some of them are close to critical infrastructure. The cumulative hazard from all of these silent systems could be far larger than anyone has appreciated. The work being done at Taftan is part of a broader scientific effort to map this hidden risk. By demonstrating that satellite-based monitoring can detect unrest at a remote, long-dormant volcano, the team has provided proof of concept for a global program. The same techniques could be applied to thousands of other mountains around the world, identifying which ones are showing signs of activity and prioritizing them for further investigation. The cost of such a program would be modest by global standards. Satellites are already in orbit. The image data is largely freely available. The analytical techniques are well established. What is needed is dedicated scientific effort and institutional support to systematically apply the methods to the full population of supposedly extinct volcanoes. A few research groups around the world have begun this kind of systematic survey. The European Space Agency has supported volcano monitoring projects that use Sentinel data to scan large numbers of mountains for signs of unrest. Academic teams in the United States, Europe, and Asia have published papers identifying previously unknown signs of activity at various supposedly dormant volcanoes, but these efforts remain fragmentary and underfunded. There is no single global program dedicated to monitoring all potentially active volcanoes. The work is being done, when it is done at all, by individual researchers responding to specific opportunities or interests. The systematic, comprehensive scan of the world's silent mountains has not yet happened. If it ever does, the results could change how humanity thinks about volcanic risk. We might discover that some of the mountains we have ignored for centuries are far more dangerous than we realized. We might find that some regions of the world, have a much higher concentration of active systems than current maps suggest. We might confirm what the work at Taftan and Mathana already hints at, that the volcanic landscape of Earth is more dynamic, more alive than we have allowed ourselves to acknowledge. The next chapter brings the story back to the mountain itself and to the question of what the future holds. When asked what will happen at Mount Taftan over the coming years and decades, scientists give careful, hedged answers. They have to. The data is too thin, the system too poorly understood, the precedents too rare for confident predictions. But certain scenarios can be sketched out, even if they cannot be assigned firm probabilities. Scenario 1 is the quiet fade. In this version of the future, the current unrest at Taftan represents a minor, transient episode of activity. The pressurized zone slowly releases its load through gradual gas seepage. The ground subsides, perhaps over years or decades, back towards its original level. The fumarole emissions return to background levels. The volcano slips back into its long sleep. Future generations look at the satellite data from 2023 and 2024 as a curious anomaly, with no real consequences. This scenario has historical precedent. Many volcanoes around the world show occasional brief episodes of unrest that do not lead to eruptions. The systems respond to subtle internal changes, generate measurable signals at the surface, and then return to equilibrium. The events are real, but they fade without major consequences. Scenario 2 is the steam blast. In this version, the current pressurized state eventually fails through a phreatic eruption. The blast is small to moderate in size, killing anyone unfortunate enough to be near the summit when it occurs, but not affecting the wider region significantly. After the explosion, the system releases its trapped pressure and returns to a state of low activity. The volcano remains dangerous in principle, but the immediate crisis passes. This scenario aligns with the Mount Taftan event of 2014. The death toll could range from a handful to dozens of people, depending on how many are on the mountain at the time. The economic damage would be limited but real, including infrastructure repairs, ash cleanup in nearby villages, and possible disruption to local agriculture. International attention would briefly focus on Iran's volcanic monitoring gap, possibly prompting some new investments. Scenario 3 is the slow build-up. In this version, the current unrest represents the early stage of a longer process. Over years or decades, the pressure beneath the summit continues to grow. Periodic episodes of inflation and gas release occur, each one slightly larger than the last. Eventually, perhaps after many years, the system produces a more substantial eruption. The size of the final event would depend on how much magma has accumulated and how the system finally vents. This scenario is harder to bound in terms of timing or magnitude. The eruption could be moderate, similar to historical events at other Iranian or Turkish volcanoes. It could be large, on the scale of a Pinatubo eruption, with regional and even global consequences. It could be small, a brief flare that gets little attention. The defining feature of this scenario is the long timeline, with continued monitoring required throughout the build-up phase. Scenario 4 is the surprise event. In this version, the current unrest is misleading. The volcano either appears to quiet down or stays in its current frozen state for an extended period, lulling observers into complacency. Then, with little warning, a major eruption occurs. The lack of monitoring infrastructure means that the warning signs are missed or misinterpreted. The eruption catches everyone unprepared, with consequences ranging from local disaster to regional catastrophe. This is the scenario that scientists fear most. It is also the most preventable. With adequate monitoring, the warning signs of a major eruption would be detectable in advance, allowing for evacuations and emergency response. Without monitoring, the system is essentially invisible until the moment of failure. Which scenario will actually unfold is impossible to know. The research team studying Taftan has been careful not to make predictions that cannot be supported by the data. They have emphasized that an immediate eruption is not expected, that the volcano is unlikely to suddenly explode in the near future, and that the appropriate response is improved monitoring rather than panic. But careful is not the same as reassuring. The team has also emphasized that the current state of the volcano is genuinely unusual, that the standard rules of volcanic classification have failed, and that the risk over the coming decades is higher than previous assessments suggested. The mountain deserves attention that it is not currently receiving. For the people of Kash and the surrounding region, this kind of nuanced assessment is hard to translate into daily life. They cannot live in a state of permanent fear about a volcano that might or might not erupt sometime in the next century. They have homes to maintain, children to raise, businesses to run, and concerns that feel much more immediate than the slow movements of underground pressure. What they need from the scientific and political communities is honest information, modest precautions, and a system that will warn them if the situation changes for the worse. So far, they have gotten only fragments of all three. The next chapter looks at the question that this entire investigation has been driving toward. What does Taftan tell us about ourselves? Throughout human history, civilizations have built themselves in the shadows of volcanoes, sometimes by choice, drawn by the rich soils and abundant water that volcanic regions provide, sometimes by accident, settling in lands whose deep geology was unknown to them. Either way, the pattern repeats across continents and across millennia. People live next to mountains. Sometimes the mountains erupt. The story of volcanic disaster is, in many ways, the story of forgetting. Societies remember their volcanoes in the immediate aftermath of major eruptions. The Roman world spent centuries discussing the destruction of Pompeii and Herculaneum. The Indonesian archipelago has a rich oral and written tradition about the great eruption of Krakatoa in 1883. The Caribbean nation of Martinique still teaches school children about the Mount Pelée disaster of 1902. But over generations, the memory fades. New generations are born into landscapes that have been quiet for so long that the volcanic threat seems abstract. Cities expand, populations grow, the land becomes valuable again, and the warnings of grandparents are dismissed as superstition or excessive caution. This pattern of forgetting is exactly what has happened at Mount Taftan over the past 700,000 years. By the time humans developed civilization, the volcano had been silent for so long that no human society had ever experienced its eruptions. There were no oral traditions about Taftan's destructive power, no written records of catastrophic events, no cultural memory at all of what the mountain was capable of doing. When people did finally settle in the region, they treated the mountain as a feature of the landscape rather than a threat. They built farms in its foothills. They established villages on its slopes. They watched its fumaroles and considered them a curiosity rather than a warning. The volcano was, in every meaningful human sense, dead. The recent satellite data shows that this assumption was wrong. The mountain has been alive the whole time, just running on a clock that operates outside human perception. The 700,000 years of silence was not the end of the story. It was a pause. This realization has implications that go beyond Taftan. It calls into question the way human civilization has approached volcanic risk in general. We have built cities, planted farms, and constructed infrastructure based on the assumption that we can identify which volcanoes are dangerous and which are not. The new evidence suggests that this assumption may be fundamentally flawed. If volcanoes can stay alive for hundreds of thousands of years without erupting, then the simple rule of looking at recent eruption history is inadequate for hazard assessment. We need new methods, better monitoring, and a more humble approach to the question of which mountains pose risks. The technology to do this exists. Satellites can monitor every potentially active volcano in the world from orbit. Ground-based instruments can be installed in remote regions with relatively modest investment. Scientific cooperation across borders, when the political will exists, can produce comprehensive monitoring networks within years rather than decades. What is missing, in most cases, is the political and financial commitment to actually do this work. Volcanic monitoring is the kind of investment that pays off over decades and centuries, not over election cycles or fiscal years. The benefits are measured in disasters that did not happen, lives that were not lost, and disruptions that were avoided. These benefits are hard to see and harder to claim credit for. They do not generate ribbon-cutting ceremonies or favorable headlines, and yet the cost of not doing the work is potentially enormous. A single major eruption at a poorly monitored volcano could kill thousands of people, displace millions, and cause economic damages running into hundreds of billions of dollars. The investment required to prevent such an outcome is a tiny fraction of the potential cost. For Taftan specifically, the path forward seems clear. International cooperation, modest financial investment, and sustained scientific attention could transform the volcano from a poorly understood mystery into a well-monitored system. The people of Kash and the surrounding region would gain real protection. The global scientific community would gain valuable insights into how long dormant volcanoes behave. Future generations would inherit a safer relationship with one of the planet's hidden giants. Whether this path will actually be taken depends on choices that are still to be made. Scientists, governments, international organizations, and ordinary citizens all have roles to play. The volcano will continue to behave as it does, regardless of what humans decide. The question is whether we will be paying attention when it does. The next chapter is the final stop in this journey, and it asks the question that has been hovering over the entire story. If Mount Taftan can wake up after 700,000 years of silence, what else is waiting? This is the question that has been driving the research, the policy debates, and the public attention surrounding the recent discovery. It is also the question that no one can answer with certainty. Around the world, in regions both well-known and obscure, sit volcanoes that have been silent for tens of thousands or hundreds of thousands of years. Some of them are famous. The Yellowstone supervolcano in the United States has not had a major eruption in over 600,000 years, and yet its system shows ongoing signs of activity, including measurable ground deformation, gas emissions, and earthquake swarms. The Long Valley caldera in California, the Toba caldera in Indonesia, and the Phlegraean fields near Naples all have long quiescence periods punctuated by smaller events. Other systems are less famous. There are mountains in Central Africa, in the Russian Far East, in remote regions of South America, in island chains across the Pacific, that have not been carefully studied in decades or longer. Many of these mountains are classified as extinct based on the absence of recorded eruptions during human history. The recent work at Taftan, Methana, and Utarunku suggests that some of these classifications may be wrong. The exact number of supposedly extinct volcanoes that are actually still alive is impossible to know without comprehensive global monitoring. Estimates range from dozens to hundreds, depending on how strictly the criteria for being alive are applied. Even if the lower estimates are correct, the implications are significant. Tens or hundreds of mountains around the world, currently considered safe, may pose real hazards to nearby populations. For most people, this information will never seem urgent. We do not naturally think about geological timescales. The threat of a volcano that might erupt sometime in the next several hundred years feels different from the threat of a hurricane next week or a wildfire next month. The brain treats them differently. The budget treats them differently. The political process treats them differently. But the volcanoes do not care how we treat them. They follow their own internal rhythms, dictated by the slow motions of magma and the slow accumulation of pressure deep underground. When they finally release that pressure, the consequences for human civilization will be the same whether we were paying attention or not. The story of Taftan is, in this sense, a story about ourselves. It is a story about what we choose to monitor and what we choose to ignore. It is a story about how we balance the urgent against the eventual, the visible against the hidden, the immediate against the long-term. It is a story that has been written over and over in human history, and that will be written again in different forms and at different mountains as long as people continue to live near the geological features that shape our planet. Pablo Gonzalez, the volcanologist who first noticed the satellite signal in 2024, has continued his work on Taftan and on other long-dormant volcanoes around the world. His team has published several follow-up papers extending the analysis to other mountains in the Makran subduction zone. They have argued that the entire region deserves more scientific attention and that the assumption of low volcanic risk in this part of the world should be revisited. The doctoral student who first looked at the satellite imagery in 2020, Mohammed Hossein Mohammed Nia, has built much of his early career around the Taftan project. His work has been cited in international policy discussions about volcanic hazard assessment in the Middle East. He represents a new generation of scientists who are pushing for more comprehensive monitoring of forgotten mountains. The people of Kash continue to live in the shadow of the volcano, mostly unaware of the international scientific discussion that has grown up around their nearby mountain. They go about their daily lives, raising families, running businesses, planting crops in the foothills. The volcano is to them just the volcano. It has always been there. They assume it always will be. Somewhere underneath the summit, 1,600 feet below the surface of the rock, the trapped pressure waits. The gas continues to flow from the fumaroles. The ground holds its 3.5-inch rise. The system is loaded, balanced, watching for whatever comes next. The mountain is awake. After 700,000 years, it remembers how to move. Whether it chooses to fully rise again in our lifetimes, or in our grandchildren's lifetimes, or somewhere far beyond, is not a question we can answer. What we can do is keep watching. The eyes in orbit will continue to pass overhead. The radar signals will continue to map every shift of the surface. The fumaroles will continue to hiss their warnings into the desert air, and the mountain, patient as only mountains can be patient, will continue to wait.